Привет всем. По-моему, русскоязычный, можно по-русски, но на всякий случай можно.
Ну, подожди еще, Жень. Во-первых, не все по-русски.
Во-первых,
Хай, тульмонд, это по-французски.
Жень, 10 минут.
Салю.
Открой слова, на всякий случай. Открой дикшенери.
Открыть.
Словарь.
Словарь?
Ну, конечно, переводить свой текст.
Так, меня видно, это и слышно.
Видно.
Я в вышке.
Пошла трансляция
Ушел в
в
вышку,
YouTube.
потому что это...
Хорошо.
Видишь, вчера как глючил-то.
Вы будете показывать?
Да, сейчас, да, у меня будет такой дешевый. Сначала куда?
Драма, дешевая драма.
Вот это вот?
Да.
Ага.
А Оленька
Мне
где
Влад
ты?
помогает.
Я дома.
Вот сюда
Дома.
теперь.
Нет, это я дома.
Вот это мой как я. Презентация.
Да,
покажи, мы не видели, Жень.
Вот я начинаю двигаться оно, да?
Да, все нормально. Ну все, ждем тогда
всё,
еще 10 минут.
Ага. Оставить или убрать, или что там?
Да, оставьте, пусть работает.
Пусть привыкают. Заодно переводишь название хоть.
Ну, тут оно, да, немного. Может, время хватит на перевод.
Окей.
У меня дома с ноутбука, с компьютера странные вещи происходят. Там почему-то мой звук, он там защемляется, как будто это самое, кто-то преграды делает. Вот, наверное, эти террористы. И я с Долгопрудным тоже практически свой доклад как бы сорвал. Там 20 минут, это было не жалко. Здесь. А тут, конечно, вот спасибо Владу Галкину. Значит, меня сюда это самое пристроил.
Алексей, меня там тоже на всякий случай кохостом сделайте, чтобы не сорвалось внезапно. Для подстраховки. Я, правда, только до 6 часов. В 6 часов я, наверное, не смогу 2 зума одновременно.
Ваня, ты говоришь, да?
Да, это я. Добрый
Привет,
день. Приветствую.
Здрасте.
Да, вот вижу тебя ковбойская такая,
Это я на Тайване. Там очень было солнце яркое.
Вид у тебя ковбойский.
Так, Жень, у тебя 40 минут, да?
Да.
А потом у нас перерыв, да, Леш? Все правильно.
Да, а потом обед.
Обед. А кто уже пообедал?
Значит, надо будет сразу ужинать, чтобы потом до вечера.
Мероприятие.
Но вчера клевый доклад у Банати был, надо сказать. Единственное, что я пытался его спрашивать во время доклада, вопросы задавать. Когда включал свой микрофон и вроде открывал рот, меня чем он выключал? Было написано, вас отключил организатор. Я вначале думал, что, может быть, он просто не хочет, чтобы я прерывал, потом выяснилось, что он мой писк выключал. Ну, конечно, жалко, что не живьем. Конференция.
Ну, ладно, спасибо, что так. Спасибо, что так.
Да, спасибо, так. Оля, а у нас будет тоже, наверное, онлайн, да? Шильниковская и Гриневская.
Да.
Их сразу 2 будет, или мы объединим?
Подряд. Ну, подряд, просто подряд.
Подряд. Может быть, через тире их написать Шильникова, Гринеса. Слав, ты не против будешь или как? Он ушел куда-то, что ли?
Не знаю.
Ушел.
Так, Жень, а ты меня видишь?
Да.
Я здесь же, я просто звук отключил, чтобы, не дай бог, что-нибудь не сказать лишнего.
Я предлагаю сделать обобщенную
Подожди, давай обсудим между собой. Давай, не надо, здесь все-таки народ. Давай.
Про конференцию я имею в виду.
Ну, правильно, ну вот, что мы, это же на весь мир транслируется.
И что?
Наш разговор. Ну, не надо.
Съедутся, заинтригуются.
Да, вот именно. Давай, потом. С Оленькой поговорим. Я хотел тебя сегодня, но подумал, что тебя не надо отрывать.
Ты хотел мне
Я
позвонить чего-то, что ли? Или чё?
Да, я только вчера узнал, сам согласовать докладчика. Мы с тобой еще поговорим. Давай.
А сейчас кто у нас чем?
Я
Нашли,
же,
да?
я,
А, ты?
я. Ага.
Мгм.
А у нас кругом свои люди.
Вообще странно, что нас не поставили традиционно в один день троих. Обычно это была, так сказать, такая,
Традиция.
как бы, да, пенка всех организаторов. Это Гринис, Починка, Жужума. В один день.
Гуревич еще, да.
Гуревич, да. Мы, так сказать, мы
А у
дружно
нас,
друг друга слушали.
у нас в этот раз расписание по часовым поясам. Приходится всех русских ставить на самое начало,
Понятно.
поэтому получилось, что все так размазались. Там сначала, значит, у нас Россия, потом Европа, потом Америка. Что делать?
Да, клево. Клево.
Да нет, так хорошо все.
Так.
А Бертрана-то мы знаем, Оленька? Он к нам не придет.
Сейчас посмотрим. Может быть,
Бертраме?
да. Нет, Бертран.
Бертран.
После тебя, который делает доклад. Бертран Дираим. Фамилия им знакомая.
Алло.
Влад, а как сделать, чтобы были все фотографии, которые есть в галерее? Я вот вижу только того, кто говорит. А как сделать, чтобы все были?
Там в углу есть
Оль, ты
кнопка.
Влада спрашиваешь или что?
Да. Ага.
Да.
В правом верхнем углу вид надо изменить на галерею.
Вид, точно. Ага. У меня здесь стандартный, а параллельный докладчик у меня есть. Вот стандартный. Вот стандартный я вижу больше людей. Это, наверное, нормально. Угу. Вот галереи мне нет. А вот есть галерея. О, есть.
Можно вообще посмотреть, кто сейчас в эфире, что ли, да, у нас?
Да, ну, по крайней мере, фотографии посмотреть. Посмотреть, кто в эфире, это можно и так, да.
Вильям Вуд присоединился, Тимур. Уже два англоязычных.
Вот я смотрю, Дима Минц вроде, Зинина Света,
Угу. Ну, как на тебя пришли.
Тимур Бакиев, Ужин, по-моему, да, как некий.
Чужин. Вильям Вуд.
Вильям, а я не вижу Вильяма.
Списочек там. Нажми, где вот эти
Он
нарисуют.
подключается просто еще. Подключается.
Ну ладно.
Участники. Нажми на участников, ты увидишь.
Я боюсь. Что я сделать?
У тебя Влад рядом, так что можно не
Да
переживать.
все равно. А мы это, кстати, Влад рядом, но хорошо, что мы заранее пришли.
Так,
224-й, там, во-первых, оказалось, что компьютер заржавел, еле-еле
Да.
пишет. Да, потом там
так, вот.
еще какие-то проблемы. Мы перебрались в 228-ю.
Технику надо использовать, это верно.
Да. Ну, там, по-моему, уже ее надо менять, что ли. Тут у нас, кстати говоря, на этаже, вот на втором этаже, все компьютеры вытащены из каких-то аудиторий, что ли. По коридору идешь, как по улице, где с обоих сторон припаркованные машины, сейчас тут припаркованы эти компьютеры и так далее.
Большое переселение, видимо. Там строят здание, это, Жень, у нас за окном-то.
Надо посмотреть, ну, видно, здесь закрыто.
Оленька, а во сколько у тебя семинар-то завтра?
В 11.
Так он закончится как раз у тебя.
Ну, где-то около часа, да, закончится.
Ну вот, а и ты можешь приходить на конференцию.
Угу. Вот,
И студенты могут. Я думаю, что так и надо сделать. Чего уж тут.
Так можно отменить. Оль, у тебя семинар-то онлайн?
Да нет, у нее все хорошо как раз. Ничего отменять не надо. У нее семинар до часу.
Угу.
Пусть студенты придут. Минц тот же придет, там все, кто сможет. И ты, главное, сама.
Хорошо, мы постараемся.
Конечно. Тебе ничего не стоит.
Ты живьем, да, Оля, я хотел спросить?
Да. Угу.
Ну, отлично. То есть я с тебя буду брать пример.
Похоже, не больно народ, и поэтому лучше хоть своим порассказывать.
Угу.
Вот.
Так.
Это учеба онлайн, это, конечно, какой-то идиотизм. И те скучно, и студентам скучно. Вот. Они так сидят друг с другом, подшучивают, что-нибудь там улыбаются друг другу, тебе поулыбаются. Вот.
Так, Жень,
И так далее. Они тусоваться должны.
Можно начинать, давай.
Да, Жень, давай. Ага. Dear colleagues, good afternoon. We continue our session, our memorial conference devoted to Dmitry Viktorovich Anosov. And our first speaker is Evgeny Zhuzhoma with talk dimension 1 basic set of R flows.
Thank you very much, organizer, especially Alexei Klemenko, for inviting me to make speech on this beautiful conference. I was several times at home, Dmitry Viktorovich Anosov, and we have several common papers, common surveys, closing lemmas, and surveys about asymptotic behaviors of one-dimensional leaves of local laminations on surfaces. And it was great moments when we discussed with him our papers, our results, and so on. And let me start my talk. I could mention one basic sets of I flows jointly with Vladislav Medvedev, and some historical remarks. Yesterday, Christian Bonatis said about what Smale in 1961 met Anosov, Sinai, Arnold, and Novikov, and talked with him and conjured some results, some ideas. And one of them was that geodesic flow on manifold of non-positive and negative constant is structurally stable. And this is true. And in 1 year, in 1962, Anosov published announced result in Soviet доклады exactly about this fact. Anosov introduced dynamical systems, which later on was called Anosov systems, and proved that these systems are structurally stable. And by definition, Anosov systems.
Женя, Anosov introduced flows also, or only diffeomorphism?
Flows and diffeomorphism together. Together. And by definition, Anosov systems means that supporting manifold, closed manifold, endowed with hyperbolic structure. That's all.
Жень, a structure is not continuously dependent from point. This decomposition.
This can be proved after. It falls from definition. Yes, good questions. It can be proved that this tangent bundle moves continuously.
If you have hyperbolicity in every point, then
yes,
it will be continuous dependence.
Yes, exactly. It is a result. And Anosov system splits into flows. That is dynamical system with continuous time, and Anosov and diffeomorphism. That is dynamical system with discrete time. In 1963, Anosov announced result what if Anosov flow has an integral invariant when periodic trajectories are dense in the supporting manifold. And all results was proved in 1967 in this journal, this paper. And one of the results, important results proved in this paper was so-called Anosov closing lemma. Christian Bonatti yesterday mentioned about this closing lemma. From this closing lemma, and follows that periodic trajectories are dense in a non-wandering set of Anosov flow. And Smale in 1967 introduced so-called axiom A system, and in short R systems. By definition, R system has a non-wandering set endowed with hyperbolic structure, and the periodic orbits are dense in the non-wandering set. In some sense, Smale generalized results of Anosov. He introduced this very, very wide and important class of dynamical systems. And due to Robinson, Manet, Hayashi, our systems contains all structural stable systems, in particular Morse-Smale systems and Anosov systems. So it's very wide class of dynamical systems. Okay. Smale proved so-called spectral decomposition theorem that says that non-wandering set of any system is the joint union of closed invariant and topologically transitive sets, which called basic sets. And we see that globally our system looks like a Morse-Smale system where basic sets not only trivial, but maybe non-trivial. A basic set by definition is trivial. It is if it is an isolated periodic orbit. And the Morse-Smale flow is a good example of a flow with trivial basic sets. Okay. I will say only R flows. And for R flows, spectral decomposition theorem was proved in 1970s by Pugh and Shoup. Smale proved for spectral decomposition theorem for diffeomorphism, not for flows. For flow, it was proved in 3 years after. Okay. And what questions we can consider about basic set of R flows? What we can say about dynamical and topological structure of non-trivial basic set of different topological dimensions, and what closed manifold admits non-trivial basic sets of different topological dimensions. And I will consider non-trivial basic sets. Not that is not Morse-Smale, and mainly I will consider non-singular R flows, because singularity is a trivial basic set of I flow by definition, must be isolated. So delete singularities, and a non-trivial basic set has topological dimension no less than 1, because trajectory one-dimensional, and the supporting manifold has dimension no less than 3, Okay. it is minimum. Let's introduce types of basic sets. A basic set is attractor if there is an attractive neighborhood of omega, such what with inclusion, holds with inclusion, and with equality. And Ft means the time shift along the trajectories of the flow. A basic set is a repeller if it is attractor for the flow where time opposite direction has opposite direction. And the basic set is of saddle type if basic set is neither attractor nor repeller. Okay. In 1975, Zeeman proved that any n-manifold and larger than 3 supporting non-singular flows supports NA flow with a one-dimensional non-trivial basic set. And note that in this case, one-dimensional non-trivial basic set must be of saddle type. Must be saddle type. It is natural to consider two-dimensional non-trivial basic sets of flows, beginning with three-dimensional manifold. And more general, it is possible to consider a codimension 1 basic set of on n manifold, on manifold. And it is easy to prove the result, the following theorem. Let omega be a codimension 1 basic set of a flow Ft on a closed n manifold. And when omega is either attractor or repeller, that is not saddle type, only attractor or repeller. For a diffeomorphism, this theorem was proved by Plikin and independently by Williams. For flow, the proof similar. Following Williams, we introduce, we will say, an expanding attractors. That means it is attractor if his topological dimension equals dimension of unstable leaves, at any point of attractor. Similar can be defined a contractive repeller. The following theorem is almost folklore. A codimension 1 expanding attractor is locally homeomorphic to the product of the Euclidean space of the dimension n-1 and counter set. So the theorem gives a local topological structure of expanding attractor. Similar for, of course, for contractive repeller of the same result. And again, for a diffeomorphism, this theorem was proved by Plikin and independently by Williams. For flow, the proof is very, very similar. It is easy to construct that in a flow on 4-dimensional manifold with a dimension 1 attractor which is not expanding. It is enough to take two-dimensional non-expanding attractor on free torus and take a suspension. However, for three-dimensional manifold, one can prove the following theorem. Let lambda R be a non-trivial attractor on a closed 3 manifold when this attractor is expanding if and only if it is two-dimensional, codimension 1. In three-dimensional case, codimension 1 means expanding and vice versa. The proof is due to the low dimensional case n equals 3. The dimension of strong unstable leaves equals 1.
Женя, it's your theorem?
Yes, it is theorem. Yes.
But repeat once more. What happens here?
Take a non-trivial attractor on free manifold, on closed free manifold. When this attractor is expanding, if and only if is the basic, this attractor is two-dimensional. That is codimension 1 in three-dimensional case, equivalent to be expanding.
Because for
four-dimensional manifold is not true, but in three-dimensional case it's true.
Also.
Because
for diffeomorphism is not such.
Yes, this result does not hold for three-dimensional diffeomorphism. Let me recall, before I said take two-dimensional attractor torus, two-dimensional torus, and three-dimensional torus, and the two-dimensional torus is not expanding. Yes.
Yes, I understand. Because all one-dimensional set for diffeomorphism on surface.
Yes.
Yes,
For three-dimensional diffeomorphism is not true, but the flow is true. And they're very, very easy to prove, because one-dimensional strong unstable leaves, dimension of one strong unstable leaves equals 1, and when unstable leaves, dimension of unstable leaves equals 2, and this means that lambda is expanding and vice versa. Okay, that's very, very easy. Okay. Now I introduce and recall the notion of mixing and non-mixing basic set. First, we take flow on some set, maybe topological, and a flow is called mixing. If given any open subsets UV, there is TO, such what one neighborhood, one open subset U will be intersect FT of V for any time beginning with TO. And at the definition of mixing, and otherwise flow is called non-mixing. Okay, on the sum set M. And a good example of non-mixing flow is a dynamical suspension of a homeomorphism. This is mistake, chromatic mistake. F of some set M. Suspension is defined on the mapping torus, n times interval of 1, and after gluing point x1 and fx of 0, 0. Okay, it is standard definition of mapping torus, and on this mapping torus one can define flow called suspension, and trajectories of this flow are formed by segments.
Why is not mixing, Жень?
What?
Why is not mixing any suspension flow?
Take any open subset, okay?
Okay.
One subset fixed, no moved, and another subset move under the flow, okay, under the flow. And because this is suspension, this this set ft from V
Мгм.
will be go any times.
Along axis Z, yes?
Yes. Any times it go
Yeah, I
from-
understand.
from
It
level
means
0
that-
to level 1 and so on. And by definition, mixing means what this intersection might be non-empty for all t, for all time.
Yes, I understand.
Yes,
Not
yes.
for
This
any
intersection
grade.
will be non-empty for infinitely many times, but
Mhm.
not all, beginning for
But
some.
what means if there are infinitely many t? What notion? It's not mixing, but what notion for such behavior?
Non-mixing?
Нет. If there is infinitely many t with such property, not all t.
It is not mixing.
Нет, it's not
in
mixing,
general.
but is there such notion? Есть такое понятие,
Какое?
если для бесконечно многих t?
I don't know. Yes, there is. It is, as I understand, it is transitivity.
Transitivity,
Yes,
yes.
it is exactly
For
transitivity.
flow also there is transitivity notion.
Yes, it is transitive. Yes.
Thank you very
If
much.
homeomorphism F is transitive, the suspension is transitive. Okay, yes, of course, transitivity. Okay. So suspension is not mixing flow. Even homeomorphism F is mixing and transitive and so on. Okay, it is a good example of non-mixing. And Bowen introduced the notion of mixing and respectively non-mixing basic sets. Following Bowen, basic set omega of n flow is mixing, is the restriction on this set is a mixing flow, and of a y is non-mixing. Okay, and good example of such non-mixing basic set is suspension over a diffeomorphism of surface M with one-dimensional attractor. One-dimensional attractor, for example, Plikin and DA attractor, and the suspension has a two-dimensional non-mixing attractor. Okay. We will consider with the attractor a basin of attractor. It is a stable manifold of attractor, and the basin consists of the trajectories those omega minimal sets belong to attractor. Certainly, basin is open set, three-dimensional open set on three-dimensional manifold. And let's consider embedding of basin and tree. Okay. Oh, before this, let me introduce and recall one more notion: a link in free manifold. A link in free manifold is a collection of disjoint nodes, L1 and K, and a link is called fibrate if the complement to this link is a total space of fiber bundle locally of total space of locally trivial fiber bundle over circle of the circle S1, and the boundary of any fiber is link. Okay, fiber of this underband is a surface, and the boundary of this surface consists of these nodes. In addition, it is by definition the fibers meet link nicely. To be precise, let's consider one node of this link, and this node has a neighborhood solid torus. Solid torus. Solid torus is a product of two-dimensional disk, which we consider like this, is a disk, unidisk, and complex plane, and circle. And we consider mapping depending Z over model Z. And it is, in addition, the fiber bundle P is coincide with fiber bundle P in this neighborhood neighborhood of each node of the link here. Okay, and this definition by okay.
It's very similar to the Seifert manifold, not? It's not.
No, not. I think not. It is very, very close to the open book decomposition.
Mm-hmm.
So fiber bundles of these fibers of these fiber bundles, goes to and looks near each node like this, like in this picture. This is node. It is axis of solid torus, and fiber bundles go to this node like book, like pages of the book. So,
but it is a complement in M3.
Yeah.
I don't understand.
Yeah.
Yes.
If we delete node, this is axis. We will have a fiber bundle of a circle. Fiber bundle of a circle, and the fibers will be with pages.
It's definition of.
Yes, and by definition, it is very, very big definition of fibered link.
Fibered link.
Fibered link, yes, with definition of fibered link. Link is the union of nodes, the joint union of nodes. But the fibered link is definition.
Вот, это meets aim nicely.
The
Yes?
complement, fibered means that the complement to this link is a fiber bundle of the circle.
I understand.
And moreover, in addition, the fibers meet L nicely. So what does mean nicely? It is exactly here below. Okay, by definition.
Okay.
Okay. And one can prove the following theorem. Let Ft be a flow on an orientable closed free manifold, such what flow has a two-dimensional non-mixing attractor, lambda r. And when there is a special compactification of the basin of this attractor by a family of circles, L1, LK, such that the following condition hold. This compactification is the union of basin and circles. It is formal union, but in this formal union, one can introduce the structure of closed orientable free manifold. Okay, the original flow on the basin is extended continuously to a non-single structure stable flow F tilde on this compactification with the non-wandering set consisting of attractor and these circles. Moreover, each circle L1, Lk are repelling isolated periodic trajectories of this flow, extended flow F tilde T. And at last, the family of these circles is a favorite link in this compactification. Okay?
Мгм.
The compactification is called casing. We will call this compactification casing.
It's your definition.
What?
It's your definition, casing manifold.
The manifold which satisfies condition theorem is called a casing by definition.
No, by definition, it's your definition.
Yes, of course. Yes, our definition. Yes, our
Yes,
definition.
yes.
And it's casing, and recall the Green's casing of his one-dimensional attractor on the surface for a diffeomorphism. You listen, Mislava?
Мгм.
Green's? No.
I hear.
Yeah, casing, it is very, very similar to yours casing of the one-dimensional attractor you introduced for one-dimensional basic sets on the surface.
А что это по-русски-то?
Носитель.
О, кейсинг. Окей.
It is in Russian носитель casing.
Мгм.
Okay?
Мгм. Окей.
And sketch of proof the following. Due to Bowen, this is paper, American Journal Mathematics, 1972. The restriction of the flow on the basic set is suspension. Tau times suspension, tau can be take 1 unit. Suspension over some so-called A-star homeomorphism. We take strongly unstable leaf, take closure, topological closure. Yes, topological closure actually is a set, and over this set, or suspension over the set, the original flow Ft is the restriction, exactly the restriction. And this allows to construct a global section surface, in general open surface, for the flow near our attractor. And on this surface, we get one-dimensional attractor, and by applying Green's theory, it follows the existence of attractor neighborhood of this attractor, such what boundary of this neighborhood is transversal to the flow and consists of finitely many two-dimensional toruses. But after that, it is easy to get this compactification. Actually,
Okay.
we glue to basin solid toruses, and get these results.
Suspension of closed curves with our basic set, we get Tarai. Okay.
Yes, exactly. And after that, it is very, very easy to get compactification we need. Okay, this is idea.
But are the examples not suspension of such dynamic?
Of course, we consider non-mixing attractor. Non-mixing. We use non-mixing. We use non-mixing because we apply Bowen results.
Yes, I understand. But if I consider, for example, suspension and surface diffeomorphism with the then I get your situation casing manifold, yes?
Not exactly.
Why? No, if I consider not exactly.
Not exactly. Let me go on with the following example. For illustration, take a DA diffeomorphism of two-dimensional torus, which obtained from classical Anosova diffeomorphism, and DA diffeomorphism obtained by Ismail's surgery near fixed point, saddle fixed point. And DA diffeomorphism has one-dimensional basic set, yes? And suspension is any flow on the wave mapping torus. And of course, on a wandering set of suspension consists of the periodic trajectory LO corresponding to sources, yes, to sources of the diffeomorphism, and two-dimensional attractor. Yes, that's it. Okay, this is simple. But this is not compactification of. This is not compactification of basin of attractor because LO is not fibrate node. This is not fibrate node. To take fibrate node, we must delete neighborhood of this trajectory, isolated trajectory, and replace by another solid torus, and one can take a fibrate node. And it is not our procedure, it is well-known procedure. But there is compactification of basin by a closed curve L, such that this compactification will be three-dimensional sphere, and this node is a figure 8 node.
But it means that it is fibrate or not?
Yes, yes. It is known that 8 node is a fibrate node.
But is it possible to understand why in suspension node is not fibrin?
Because there are no this open book structure.
Why?
Fibers will go to this node transversally. Not like here, transversally.
But what is fibers for not? What is fiber dynamically? What is fiber for this construction?
Fiber for this it will be here. Fibers for it will be surfaces. We know 1 point.
With no 1 point?
We know 1 point, yes. We know 1 point. Surface, we know 1 point. And we'll go to LO, transversally, not like here. Surfaces must go to node, like in this picture, open book decomposition, not transversally.
But is this?
This is not transversal approach.
Yes, I see.
Okay.
But these pages will be manifolds, invariant manifolds for flow or not? We have to think about these pages as invariant manifolds.
Not necessary. Not necessary. Not necessary. No. It is topological notion. Fibrate link, fibrate node.
Not invariant with respect
Not
to
invariant.
flow.
Yes, not invariant. This is casing, and that's all. On this casing, we get an structurally stable non-singular flow. Flow is a type of saver, north saver or attractor repeller. You like said that dynamical system, attractor repeller type, attractor and repeller.
You have 1 minute.
Oh, okay, sorry, just okay. But I with this is 8 knot, and there is one can prove the in sense vice versa theorem, inverse theorem. Take a favorite link on some closet orientable free manifold. When there is a non-singular A flow on M3, such as the non-Van set consists of contains two-dimensional non-mixing attractor and the repelling insulated period trajectories L1, LK.
Only attractor and
not only contains. Contains. Maybe another attractors, maybe another basic sets. This contains. But this theorem allows to prove this corollary. Given any closed orientable free manifold, there is a non-singular flow Ft, such as a non-Van set contains a two-dimensional attractor. So any three-dimensional manifold admits a flow with two-dimensional attractor. This is corollary from this theorem, and all result by American topologist Alexander almost 100 years ago proved that any closed orientable free manifold admits a favorite link. On any orientable free manifold, there is a favorite link. So this theorem gives, and Alexander result gives this corollary. In particular, in sphere, three-dimensional sphere. In three-dimensional sphere, there are no A diffeomorphism with two-dimensional basic set. There are no, but flow exists with two-dimensional basic set on any, including three-dimensional sphere. The sketchup proves the following. We have mapping torus because we have a favorite link, and this mapping G can be replaced by diffeomorphism, A diffeomorphism with one-dimensional attractor. This result by Newhouse, Real Tackets. And that so suspension of this G prime diffeomorphism give us the A flow with two-dimensional attractor. Okay, this is ideal proof. Very clear. Okay, and just I finish in 2 minutes. And casting is a good thing because we can take a pair of casing and favorite link. What is called, this pair is called characteristic pair, and this pair, one can prove that this pair is invariant of conjugate of flows. The conjugation of flows here, definition conjugation of flows, this is actually conjugation with every time t, okay? And one can prove the following theorem. Let Fti be a flow on a orientable closed free manifold, such as the Van set contains a two-dimensional non-mixing attractor lambda I equals 1, 2. If this restriction of flows on its basins are time shift conjugate or simply conjugate, when there are homeomorphism of this pair to this pair. So homeomorphism basin to basin, casing to casing, casing to casing, and link to link. That's all. And I finish, actually. Thank you very much for
Thank you very much. Let's thank speaker. Then other question.
It's good.
It's not a question.
Very clear, no question.
Жень, is it not mean last theorem that on manifolds there is unique such flow?
Sorry, sorry.
No, if you fixed two-dimensional basic set, it means class of conjugacy, and fixed manifold, then there is unique flow with such description. Is it follow from your theory?
What does mean unique flow? You mean
Up to equivalency or conjugacy? I don't know what is.
Up to equivalent. So take the same manifold. You mean that?
Yes, yes.
Take the same basic set. I think no, because actually we can add many other basic sets and so on. Globally, flows are not equivalent.
For example, if you know that additional basic sets only trivial periodic repeller.
A good question. I don't know.
You don't
good
know.
question. This is an invariant of conjugacy. We see this is invariant conjugacy. We can see.
But we need conjugacy.
But the proof to what equivalence of the flow, it is. I don't know what is problem. I don't know exactly. I don't know the answer.
I understand. Thank you very much. Any other question? There are no questions. And then we thank speaker again.
Thank you very much.
And we have a break up to
I must
up to 4
stop
p.m.
demonstration. Yes.
Yes.
I must stop demonstration. Yes.
Yes. And we have a break.
Okay.
Up to 4 p.m. Yes.
Yes, up to 4 p.m. Moscow time.
Moscow time. Yes. Thank you very much. See you later.
Ну, славьте Господи, а то я дома не смогу провести.
Жень, хорошо. Спасибо, дорогой.
Нет, вчера я прям в шоке был, когда я вопрос задаю Бонати, и не могу это сделать. Это, конечно. Причем я ему хотел задать вопрос во время доклада, потом смотрю, меня этот Чемэн отключает. Думаю, в чем дело?
Можешь говорить по-английски, нас, по-видимому, слушают сейчас еще участники конференции.
По-английски я не смогу, так сложно говорить.
Так а что-то я вот не понял в последней теореме, чего требуется-то. В смысле, ты какие сдвиги-то рассматриваешь? В бассейне? Вот если на последнюю теорему посмотреть.
Да. То есть я смотрю вот что. Я смотрю ограничение потока на бассейн. Это раз.
Так.
И рассматриваю, когда два таких потока на своих бассейнах сопряжены.
Именно при каждом Т, да?
Да, сопряженность, не эквивалентность, а именно сопряженность. Это то, что рассматривало поле с круглом, маленьким круглом. Да. Так что им, может быть, даже это интересно, потому что, получается, это инвариант. Вот. И доказываю, что если они сопряжены, то, оказывается, это проверяется чисто топологически. Это проверяется так, что должны быть...
Нет, тогда можно продолжить на все замыкание, да, на весь кейсинг, да?
Да, правильно ты говоришь. Это правильно. Это на носитель. То есть топологически проверяется просто. Носитель должны быть гомеоморфны. И при этом гомеоморфизмы должны переходить из зацепления в зацепление. То есть очень просто. То есть если у тебя это топологически, это получается какой-то топологическая такая проверка, а если она у тебя не проходит, ну, наверняка они не сопряжены. Вот.
Ну, я тебя еще поэта. Я просто не стал уж дознаваться, так я хотел спросить.
Ну, нормально, а что? Ну, по-русски, конечно, легче объяснять.
Легче объяснять, да. Не объяснять. Окей. Ну, молодец. Спасибо. Thank you very much.
Вот пробуй.
Имеешь честный перерыв.
Ой, не
Ты
говори. Прям я так рад.
Да.
Потому что я почти как ты ночь не спал. Думаю, что же делать-то? Как же я выступать? Вот.
В смысле чего?
Ну, я вчера понял,
А,
что
да,
меня не фурычит.
вообще беда, это очень
На
жутко.
самом деле никто не знает почему. Ни Влад не знает. Он говорит, я не знаю, что делать. Что-то там с техникой никак, не знаю.
Мгм. Ладно, давай, дорогой, сделаем перерыв. Пока.
Давай, пока.
Пока.
Петя, привет.
Здравствуй, Оля. Я тебя видел полчаса назад, только не догадался зайти через вот это вот такое официальное приложение. Я слушал где-то там через
Такой
трансляцию. У меня был вопрос к
Ага.
докладчику. Я не мог его задать, но сейчас, наверное, уже...
Ну, можешь пока спросить, еще 10 минут есть.
Но
Я
его
ему
нет.
передам.
Нет, вот там строил двумерные базисные одномерные базисные множества, да, и строил вот эти W, это сепаратристные эти самые...
Да, какие-то книжки, да. Ага.
Вот. Но правильно я понимаю, что если он возьмет одномерную картинку, там эти сепаратристные книжки будут одномерные, а эти базисные будут нульмерные. И потом он возьмет поток, эти базисные станут расслоенными, ну как-то, да? А вот эти одномерные превратятся в двумерные. Или у меня неправильное понимание?
Нет, мне что-то кажется, он не так делал.
Но он двумерное построил.
Да.
Ну вот я
потом...
хотел уточнить, как. Я
как? Он его просто надстройкой строил.
Что там двумерное в его примере? Вот он взял узел расслоенный, который... Динамика – это просто вращение вдоль узла, вот, как магнитный потенциал, значит, вокруг узла вращается. Вот динамика. Что там двумерного? Вот будут точки притягиваться по двумерным поверхностям к этим одномерным вот этому линку, да, который ториком окружен.
Само это множество будет инвариантное двумерное, по которому траектории будут мотаться, вот это вот базисное множество.
Ну, базисное множество.
Из его окрестности будут идти...
Вот можно объяснить, как это базисное множество устроено. Сам линк – это базисное множество, правда? Он инвариантный.
Да, это периодическая орбита, это периодические орбиты источника.
А что еще в это двумерное множество войдет?
И входит у него... Нет, они в одномерном, это одномерные, вот эти линки, это одномерные базисные.
Я хочу спросить про двумерные, откуда он их взял?
А двумерные, ну вот как он берет? Берет Дирайт-Фурманосов на Торе, например. И берет надстройку над ним. Вот ты
у Аносова он одномерный, да, будет?
У Дирайт-Фурманосова одномерный, да.
У Аносова вот эти W одномерные.
Да, у Дирайт-Фурманосова, не Аносовского, а у Дирайт-Фурманосова одномерные. Ты берешь надстройку над ним.
Можно узнать, вот у этого Дирайт-Фурманосова, вот что это, как геометрически эта одномерная штука выглядит? Вот там есть пример, этот самый деформация.
Петя, за 1 минуту это не расскажешь. Вот, давай.
У нас не одна, у нас больше.
Как? Откуда?
Нет,
8.
Владимирович, здравствуйте. Рассказать можно, но понять нельзя. Вот.
Нет, рассказать можно.
Человек обдумал, можно.
Надо начать с Аносовского. Возьми Аносовское отображение на Торе.
Да.
Двумерное отображение на Аносов. И ты берешь над ним надстройку. Над каждой периодической точкой будет периодическая траектория. Этих периодических траекторий четное множество. Светловых
Понятно.
Потом надо понять, что такое Дирайт-Фурманосов двумерный. Там есть так называемые граничные периодические точки. Они превратятся в периодические орбиты. И для начала надо понять, как у Дирайт-Фурманосова у отображения точки в окрестности себя ведут.
Нет, пока что понятно.
Что это за объект, а потом ты будешь понимать, как это уже для надстройки. Поэтому я почему вмешался? Потому что я же знаю, что это нужно делать последовательно и потихоньку. А так это сразу не поймешь. Надо же надстройку понять.
Нет, я это забыл просто. Я это все знал.
Конечно, ты забыл.
Я хотел немножко вспомнить. Вот, ну ладно, вы мне...
И в этой периодически Дирайт-Фурманосов, там внутри точка сидит, ну вот Фрам Дирайт, и в него втыкаются 2 сепаратрисы.
Ага, да. Вот я теперь понял.
Эти сепаратрисы превращаются в устойчивые многообразие.
Замечательно, да. Теперь стало понятно. А то картинок не было уже, ни картинок не было. Я там потерял.
Это же траектория-то у него там, периодическая траектория у него будет источниковая периодическая траектория, понимаешь, для потока-то. А эти вот про те многообразия, которые он говорит, там, где вот книжка получается, это из граничных этих точек идут надстроечные слои. Поэтому это надо все порисовать. Это совершенно безнадежно так.
Нет, очень понятно теперь стало.
Понятнее, да? Ну, я рад.
Понятнее. Я это самое, я просто хотел уточнить. Спасибо. Нет, ну порисовать, конечно, можно.
Мы же с тобой в одной в этом гранте, надо же пояснять, что делается.
Да, надо что-то пояснять, а то так это самое совсем
Витя, здравствуй,
закислись. Да, надо закислить.
Вить, здравствуй. Что-то нет докладчика у нас.
В смысле?
А,
Следующий докладчик я через 5 минут.
Ой, а не Деруан сейчас? Я что-то уже перепутал.
Нет,
да,
а Деруан после меня. Нет, я все
подожди,
перепутал.
правда, да? То есть сейчас Витя будет докладывать, да?
секунду.
Давайте проверим.
Было вроде наоборот с утра.
такого не было.
Так, schedule table. А, нет, извини, да, Деруан сначала. Может, он не сюда посмотрел? Давай ему позвоню просто.
Вот,
У меня
да,
есть его
да.
сотовый.
Он со временем
Ты
может
пришел.
перепутать что-нибудь, да.
Так. Ну, если что, нас можно поменять.
Ну да.
Ну, и как это, конечно, неудачное решение, но...
Ну, какое-то.
Holomorphic foliation, structural stability, это Аносов conjecture.
Как правильно-то произносить, Леша, фамилию-то Дераин?
Деруан.
Деруан, да? Бертран Деруан, да? Спасибо.
Да, все правильно.
Лешенька, привет.
Привет.
Ну, откуда Деруан? Здравствуй, Леша, дорогой.
Здравствуйте.
Ты из России или из...
Из Леона сейчас.
В Лионе, вот это. Я просто... Шифонеры все похожи, поэтому...
И книжки также выглядят, да?
Привет супруге передавай, дорогой.
Большое спасибо. Тоже передайте привет.
Танечка, ладно. Надо ей показать тебе. Ну ладно, потом. А Бертран-то он где?
У меня пока неудача. Я дважды позвонил, дважды гудки и автоответчик.
Он в каком городе?
Париж.
Он в Париже. Ага. Просто в том смысле, чтобы ближе там. Все-таки одно дело из Нижнего Новгорода звонить, другое дело из Рена.
Ну, Москва, конечно, ближе Нижнего Новгорода. Нет, но у меня роуминг просто. У меня просто на французском мобильнике включен роуминг, так что...
Вот так.
Разница.
Пришел.
Точно.
Привет, Аносова.
Да.
Attendez. Hi, everybody.
Bertrand. We are glad to see you.
Yes, I'm sorry I was not able to attend to the
Je
conference.
suis au revoir, mon cher.
Thank you. Thank you, Yuri.
Let's try to share your screen.
Okay. Yeah. Do you see?
We see.
Okay.
Thank you very much. It's okay. Then, good afternoon. We can start. We will continue our session. And next speaker, Bertrand Diroin.
Okay, thank you very much for giving me this opportunity to speak to this conference in honor of Dmitry Anosov. So I chose to talk about a subject that I talked about several times already. The last one was in Yulich seminar last year. And the talk, unfortunately, is going to be quite similar. Also, in the meantime, we have done some improvements with my collaborators. So I'm going to try to give you an idea about what are these improvements and what are the theories for those that have not attended to my talk last year. So the topic is holomorphic foliations. So by holomorphic foliations, I'm referring to differential equations on algebraic manifolds in the complex domain. And I'm going to speak about the subject of structural stability of these objects, which can be thought as being dynamical objects. And I'm going to speak about what I called in the title Anosov's conjecture. So maybe one of Anosov's conjecture. In fact, I'm not really sure this is a conjecture that he really did or wrote somewhere. Maybe this is just a question of him. I don't really know. This is a question about the topology of the solutions of differential equations in the complex domain. So I'm going to state more precisely what was the conjecture and try to speak about some very, very past results that we got around this topic. Right. So my collaborator is Aurélien Alvarez. He is now professor at the École Normale Supérieure de Lyon. So this is a long-term project where we study these questions of dynamics and geometry and topology of differential equations in the complex domain. So I would like to make a review of the subject. I think it would be helpful for those that are not very familiar with the differential equation in the complex domain. So the basic example, the most simple example, non-trivial example, is to consider an ordinary differential equation in the complex plane C2, which is given by a vector fields with polynomial coefficients. So here you see it's given by a differential equation where P and Q are polynomials in the variable U and V. And so you consider this differential equation, and in fact, in the beginning of the 60s, Uday Vrenov proved a very impressive theorem that says that if you choose P and Q generic among the set of degree D polynomials, so D is a fixed integer, so then every solution is either a point of equilibrium, so it's a point where P and Q vanish, otherwise the solution is dense in C2. And so it's a very impressive theorem because it contrasts a lot with a real situation where we know there is a Poincaré-Benedictson theory that says that the solutions are accumulating to periodic trajectories or periodic cycle of saddle connections or equilibrium points. So here we see that in general, the solution is going to be dense. And a little bit later, Yulich proved a very nice improvement of that theorem of Uday-Vrenov, which is that additionally to the minimality of the solution, so the fact that the solutions are dense, we can establish that in fact we have ergodicity, namely that we cannot find a partition of the phase space into two measurable sets of constituted of union of solutions of the differential equations, which have positive measure both of them. So it is ergodic. And also, which is more related to the subject of the talk today, it is locally rigid, namely that if you consider two of these differential equations that are close enough, if you can find a homomorphism that sends solution of the first differential equation to solutions of the second, in fact, you can find one which is affine, an affine map of C2. So it's a very strong rigidity result. So these two very, very important theorem was later improved in the following way. So maybe I should explain that when you take a differential equation with P and Q as before generic, then you can compactify the affine space C2 into the projective space, and the differential equations that you had compactify as a foliation of the complex projective plane, which for which the line at infinity becomes a leaf. So it becomes a leaf apart from a finite number of points which are singularities of the equation. And in fact, I should say that the proof of the Udaj-Verenov theorem and Ilyashenko theorem consists in using the monodromy of the equation at infinity. But I will not speak about it. These differential equations have a line as an invariant curve when we compactify them to the projective space. And in fact, in general, if you take a foliation of the projective plane or space, there is no reason why it should preserve a line. In general, it preserves no line, and even more, it preserves no algebraic curve. So the technique of the monodromy was not completely easy to use in this context, and this was done by Franck Loret and Giulio Rebello, who proved that there exists some open subsets in the moduli spaces of degree D algebraic foliation of the complex projective space of dimension n. So non-empty open subsets consisting of foliations that are minimal, so all the leaves are dense, ergodic, and locally rigid. So in this more general context, the same result can be established. It's almost the same in the sense that it's the same, so the same conclusions, but the open set is not dense. Maybe it's a very small open set in the moduli space, but still in such a non-empty open set, we can establish the same conclusions. And so the proof, in some sense, has some similarities with the techniques that was used by Udaj-Verenov and Jülich, in the sense that they study so not a group of germs of diffeomorphism, but a pseudo group, and they kind of establish that this pseudo group is non-discrete by using a technique developed by Gis in the 90s, which amounts to prove a nonlinear version of Zassenhaus lemma. So the theorem that we proved with Aurélien is that, in fact, there is also, in this more general context of foliations of, say, the complex projective plane, there is a totally different behavior that we can see. Namely, what we established is that there exist some stability components in the moduli space of foliations of degree 2 of the complex projective plane. And in fact, we conjecture that this stability component exists in any degree, even so we don't have a proof, rigorous proof right now. But we can see them in degree 3, 4, etc. Till I think we have done till degree 9. We can see them. So precisely, if you consider this this homogeneous vector field on C3, which is called the Jouanoglu vector field, you see it is homogeneous, so it induces the phase space is invariant by multiplication by the scalars. So it induces a foliation of the complex projective plane. And what we prove is that this foliation is structurally stable in the sense that if you move a little bit the coefficients of the equation, then you get a foliation which is topologically conjugated to the original one. And moreover, as is usual in the theory of structural stability, the conjugacy, which is a homomorphism, can be chosen close to the identity in the uniform topology. And I should say that I was speaking about the algebraic curves or algebraic solutions of the differential equation. So if there are some algebraic solution, we can use this idea of using monodromy groups, as was used by Uday-Verenov and Mulich, to prove that in fact the equation is rigid and minimal, etc. In fact, this topic was developed by Gomez-Mont in the 80s and Laura Ortiz. So they have more generous. It says that this differential equation, Jouanoglu equation, is the first equation that was founded where we know how to prove that there is no algebraic solution at all. So it's all the solutions of this differential equation are transcendental. So it was proved by Jouanoglu. So this is the reason why we call this equation the Jouanoglu equation, because it was the equation that was founded by Jouanoglu to prove, in fact, that was used by Jouanoglu to prove that a generic degree D foliation of the complex projective plane do not have any algebraic solution. Okay, so this is the first result that we prove. But also there is a nice feature about this equation is that it has a non-trivial decomposition into a Fatou set and a Euler set. So namely, so first it is not rigid because it is structurally stable, but also it is not minimal, and in particular it will not be ergodic with respect to the Lebesgue measure. So let me just say that there exists a very nice thing, that there exists an open set in P2, which is invariant by the Jouanoglu foliation. So namely, it is a union of leaves. And on this subset, we can define, we have a first integral, so a function which is constant along the solution, which is holomorphic, and which takes values in these very nice holomorphic curves, which is a Klein quartic. So it is a curve of genus 3, which has this equation. So it's very famous because this is a curve of genus 3 having the largest group of symmetries in the term of cardinality. And so on this domain, which is invariant, we have this first integral with values in that Klein quartic. This is a surjective map. And in fact, this map makes this domain, this Fatou domain, we call this the Fatou domain. In fact, this terminology has a real meaning. It makes this domain, so the foliation in this domain has the structure of a non-isotrivial fibration by disks over the Klein quartic. So we have this domain which shows that first of all the leaves, because of the fibration structure, they are closed inside this open set. So the leaves goes to infinity inside this open set. So the leaves are not dense in P2. They accumulate into the boundary of this set. And in fact, the boundary of this set, which we call the Julia set, again, there is really a meaning that I will not develop here, but the Julia set has a very much more complicated structure. I will not really say more about that, but what I just can say is that we have a conjecture made by experimental evidence, which shows, so we have a model, a very simple model, quite similar for those who know to the models that have been developed to understand the Lorentz equation. So the Lorentz equation is a differential equation in the real three-dimensional space, which is given by this equation. And it has an attractor that it's a compact subset of the three-dimensional space, which is depicted in the figure here. It's a very nice attractor. And there are some models, probably many of you knows these models, and in fact we can so we have some models. What I can say is that we have some models for the Julia set of this journal equation, which are quite similar to those models. I don't want to go into that because I will not have time. But I think this is interesting to know that there are some, so at least conjecturally we can describe this limit set. Also, what I would like to know to say is that if this model is true, in particular, Julia set of the Julian foliation, he's transversally a Cantor set, so it's locally it has the structure of a lamination, namely the product of a disk. So the disk direction is the direction of the leaves by a certain compact set in the transversal disk, and this compact set is a Cantor set. It's totally discontinuous. And in fact, if this model is true, so we have this. So we have that this is transversally discontinuous, as I said, and also we have that the Lebesgue measure of this Julia set is 0. So again, we don't know how to prove rigorously. We just have the belief by experimental evidence, sorry, that this is true. But so it would be very nice because it would prove that apart from a set of measure 0, we have a first integral. So we have a kind of integrability of the equation. Okay, apart from a set of measure 0, on which, of course, the dynamics is quite complicated, but we have this kind of integrability. And of course, what I should also say is that because of structural stability, when we move a little bit the equation, there will still be a Fatou component, okay, on which we will have a first integral with values is in another curve of genus 3, which will no more be the Klein quartic a priori. But this, I mean, all this this topological feature is going to be preserved by structural stability. So we'll get all these things also after a little perturbation. So you see that in the stability component of the Juan foliation, so namely by stability component, I mean the set of foliations in complex projective plane that are topologically conjugated to the Juanolu foliation. So we have a very different behavior than the one that was depicted by the Udash-Verenov, Ulich, and Giulio Rebello and Franck Lorez theorems. Okay, so let me come to this Anosov conjecture. I forgot to put a S here. So this conjecture says that a generic. So if you look at the set of foliations of the complex projective plane, so I remember that, just to say, I remember that I first heard about this question by Yulich that was doing traveling in Lyon, maybe in 2001, or I was in PhD, so maybe 2000, I don't remember exactly. And you told me about that problem at that time. I remember well this moment. But as I said, I don't know if there was any writing of Anosov about that. Maybe it was just an oral conjecture that was transmitted by not by papers, but in the cafe, in the cafe break, and etc. But anyway, so the conjecture, let me call that the Anosov conjecture. So that the statement is that a generic degree D foliation of the complex projective plane, if you take a leaf, it's going to be a simply connected Riemann surface. So it will be topologically a disk. Apart from a countable number of leaves, which are not topologically homomorphic to a disk, but to annuli. That is the statement of Anosov conjecture. So in a sense, what you see are, as for the topology of the leaves of a generic foliation, is the simplest logical type of surface that you can imagine. So there are very interesting theorems that I will not describe by Etienne Gis, who proved that in fact, if you take foliations by surfaces, generically the leaves belongs to a certain types of topological type. There are 6 types that you can see. So of course, you can see the disk, the annulus, but you also can see a sphere minus a counter set, a sphere minus a counter set to which you have glued an infinite number of handles and an infinite ladder, and maybe I forget one. But so there is a very nice theorem by Etienne Gis that was that he proved in the category of measurable category. So namely, he proved that if you take any foliation, so then most of the leaves, so most means with respect to some natural measure, belongs to this 6 topological type. But there are 6 topological type, and in Anosov conjecture, you reduce to 2. Of course, if you allow to move a little bit the coefficients of the equation. So what I would like to say, the reason what I speak about this conjecture here is that we are able, so first of all, this is because of the celebration of Dmitry Anosov, but also this is because we are able to prove that the Jouannou foliation in degree 2 satisfies that conjecture. So namely, we are able to prove that every leaf is a disk, so, or an annulus. So in fact, you see, just I mentioned that because I think maybe it should be clearer. So I already said that the leaves in the Fatou components are disks. So I said that the fibers of the first integral with values in the Klein quartic are disks. So they are leaves that are already simply connected. So we find that the leaves in the fat2 component are simply connected. But in the Julia set, we will find a countable number of annuli, as was predicted by Anosova. So these leaves, these annular leaves, lie in the Julia set of the equation. Right, and of course, the same. So we conjecture that the same is true for, in fact, for all the dual foliation of any degree. So if I go back here, so of course, when you define the dual foliation, you can replace the square by any power of the coordinates, but you still use the same d-symmetry. So say dx over dt is going to be y to the power d, and the same for the other coordinates. So you define in this way a degree d dual foliation, and we suspect that these foliations are also structurally stable, that they have the same kind of decomposition into a flat2 component in the Julia set, and that the Anosova conjecture is going to be true for this. Okay, so let me just so that I spoke about that last year, and in fact we have, so in the meantime we have had some improvement about our criterion, and we have a very general criterion which permits to establish that a foliation, holomorphic foliation on a complex surface, complex compact surface, has all these properties that I talked about. So let me just try to spend some time to describe these criteria. Okay. So let me say what is the setting. Okay. So as I said, what I'm doing now, I would like to describe for you a general criterion, and which is going to ensure that a foliation on a compact complex surface is structurally stable, and that it has a decomposition as before, as a Julia set and a flat2 set, and that it satisfies the Anosova conjecture. So you start with a compact complex surface. You consider on that compact complex surface a holomorphic foliation with hyperbolic singularities. So hyperbolic singularities, what I mean by that is so that the singularities are linearizable, and that can be put in diagonal form, and that the quotient of the two eigenvalues, which is a well-defined invariant up to inverse, is not real. Okay, and in fact, it is very easy to see that. So using the Poincaré linearization theorem, that those singularities are the only singularities that are structurally stable. So namely, if you move the equation at the neighborhood of the singularity, you will get something which has the same topological portrait. Okay. Otherwise, for other kind of singularities, they are not structurally stable. So of course, this is not a very important hypothesis, because if we want that the foliation is structurally stable at the end, of course we have to assume that locally at the neighborhood of the singularities, the foliation is structurally stable. So this is what we do. And now M is going to denote a Hermitian metric on the normal bundle to the foliation. So here I should say something which I will not really emphasize on that, but just I want to say that the normal bundle to the foliation, a priori, it's a bundle which is defined on the regular part of the foliation, but it is well known that we can extend this bundle naturally as a bundle defined on the whole complex surface, including above the singular. Okay, so of course, in the regular part, it has a very geometrical meaning. This is just the quotient of the tangent bundle to the surface by the tangent bundle to the foliation. And I mean, this geometrical meaning is no more valid at a singular point, right? But you can still extend the bundle as an abstract bundle, okay? And so this Hermitian metric, I just say that this is a metric on this abstract bundle in the usual sense.
And
is there a question?
And what is the leaf over the singular point?
So there is no leaf at the singular point. I just say that so at the singular point, the leaf is, so that would be the singular point. There is no leaf. But what I just want to say is that the normal bundle to the foliation can, which is a priori defined on the regular part, so apart from the singular point, it can be extended naturally as a bundle, which is also well defined at the singular point, even though you do not have any more this geometrical meaning that this is a quotient of the tangent bundle of the surface by the tangent bundle of the foliation. It's not really important. I think it's not really important to say that.
Okay.
But I just wanted to say that there is this bundle which is well defined, and we take a Hermitian metric on that bundle, right, which is smooth. Okay, so now here is the criterion. Okay, so the assumptions are in black and the conclusion are in blue. Okay, so this is the reason why there are some colors. So this is the code. So first of all, let me just describe take some time to describe the first sentence. So I'm infinitesimal distances between the leaves, right? So what does it mean? So if you think of what is a transverse metric, so a metric on the normal bundle, in fact, this metric, what really what you can do with that metric, I mean, you can do plenty of things, but one of the things that you can do is that you can measure the infinitesimal distance between two leaves. So suppose you take a leaf and you take a family of leaves that tends to that leaf that you have chosen. Okay, then you can measure what is the infinitesimal distance between between this family of leaves that tends to your leaf that you've chosen at the beginning. There is a very rigorous way to speak about that, is to take the what is called the Bode connection. So the Bode connection gives you, this is a flat connection along the leaves of the foliation, the connection which is flat along the leaves of the foliation. So you can, this is a connection on the normal bundle, and you can look on each leaf, you can look at a flat section of that connection and take the norm with respect to the Hermitian metric of that section. So this is another way which is more rigorous to speak about the infinitesimal distance between the leaves. So the infinitesimal distance between the leaves are functions on the leaves. Okay, if you take a piece of leaf, you will get some function which is infinitesimal distance. Of course, it is not a function which is univalued. So because there is the holonomy, so when you come back to your original position, it is possible that this function changed values, but locally they are well defined up to multiplication by a constant. Okay, so the critical points are the critical points of these functions, these locally defined functions. And the assumption is that these critical points, they have, so they are non-degenerate, and they are local maxima. Okay, so namely, if you see two leaves, so infinitesimally, maybe so they will. So let me just. I don't know. Yeah, you will not see.
Yes, I can see the tape. The black box.
You can see?
Yeah.
So the solutions might look like this. So you see here, for instance, you will get a local maximum. So this is a flat section of the normal bundle. So those are the leaves. This mean a flat section of the normal bundle along the leaves, and you see here there is a local maximum. Okay, but you cannot have in the assumption you cannot have a local minima like this. That would be that picture, or you cannot even have a saddle, because here this is a one-dimensional picture, but you could imagine that you have a saddle because the leaves are two-dimensional real surfaces. So you could have also a saddle, which you suppose you do not have, right? But a priori, you might have this kind of saddle. So you assume that you have only local maxima, okay? And so just with this assumption, you can prove that the existence of this flat two component. So what will happen is that if you look at the set of local maxima, so here it was, so here maybe this was a leaf and this was an infinitesimal leaf. But in the general case, what will happen is that you will get something like this, for instance, and you will get a surface of local maxima. So this is a real surface made of all the local maxima, all the critical points along the leaves which are local maxima. Critical points of the infinity distances between.
Bertrand, maybe you stop the demonstration and then we have a larger video.
Yes.
Sorry?
Maybe you stop the demonstration of your slides and then we will see much better what you write on the blackboard.
Yes.
Okay.
Yes. I see.
So I just stop like this.
Okay.
So what I was just saying is that here you have the leaves of the foliation, okay, and you can look at a real surface which is going to be transverse to the foliation, and which is the set of all points that are critical points of the infinitesimal distances between the leaves. Okay, this is that surface which is transverse to the foliation. Okay. And in fact, that surface, because of transversality, is acquiring a Riemann surface structure, which is given by the transverse holomorphic structure of the foliation. Okay. And what we prove is that in the assumptions that I described in the criterion, we can prove that the union of leaves passing through this surface is a two component, exactly as I was describing. So namely what we prove is that, in fact, if you take a leaf passing through a critical point, it's going to be a leaf and it's never come back to that surface. So it's really, I don't know, so yeah. It intersects this surface into just one point, and this surface, this leaf is a disk, And the union of all these disks describes for you a vibration by disks over this Riemann surface in green that I pictured. So this is more or less the idea that you might have about this how appears these Fatou components. Let me just share again the screen, and maybe I will come back to the blackboard later. So you get a Fatou component, and also if you assume moreover that, so of course I said again that the singularities of F are hyperbolic. I already suppose that. But assume moreover that the foliation do not have any elliptic leaf. So this is an additional assumption that we have to make. In fact, we do not have any example of a foliation that has all these. So in general, in the examples, it's possible to disprove this assumption. So to prove that there is no elliptic leaf. But so with this assumption, we can prove that F is structurally stable, and that moreover it satisfies Anosova conjecture. Okay. So let me just comment that this assumption about the existence of the non-existence of an elliptic leaf is not a very strong assumption, because it's quite easy to prove that the foliation do not have an elliptic leaf in general. But anyway. Okay, let me just take, so there are 4 minutes. So let me just pass through that. So that was just a slide that was explaining how the Juanolu foliation fulfills these assumptions, but let me just pass over that, because it's quite nice, but I would prefer to say what is the idea of the proof. So let me just spend the few minutes that I have to speak about the idea of the proof. Okay.
Yes.
So what I want to say is that the crucial idea in an object which is associated to the foliation that we call dilatation vector fields. So a dilatation vector field. So this is a real vector field on the complex surface, which is tangent to the foliation F. Okay. And dilatation means that we want that this vector field, so this is its trajectory lives in a leaf of the foliation F. So we want that transversally it's expand the Hermitian metric on the normal bundle. I'm going to switch to the blackboard. Okay.
Okay. It's okay.
So dilatation. So this is a vector field along the leaf. So if you have, of course, I'm going to describe first a picture. So this is a vector field along the leaves, which is a real vector field. This is a real vector field, which is C infinity on S, which is tangent to the foliation F. And so what we want is that along the trajectories, when we look at the normal direction, it expands. So the trajectories starting at two infinitesimally close points, which are transverse to the foliation, they are going to be to be delayed as in the picture. Okay. Of course, the leaves are two-dimensional, so it's kind of difficult to make a picture, but maybe I can try. So this is a leaf of F. Here is another one. So it might diverge in some direction, and in some other direction it converges. So here is a dilation vector field, right? So along these directions, so you see that the leaves of the foliations, they are diverging to each other, from each other. Okay. So let me just say that this concept was used, and I read that when I was PhD student, actually, in a paper by Bonatti, Langevin, and Moussu, that was published in the Journal of the EHES, and where they proved some theorem about minimal exceptionals of holomorphic foliation of the complex positive plane, and they used, in some sense, a kind of special dilatation vector fields. But here we are going to consider them, to consider all the possibilities of dilatation vector fields that we can. And the point, so of course, you see, if you consider a dilatation vector field, by the very definition, you have some hyperbolicity, because you know that the trajectories are diverging in the transverse direction to the foliation. Okay, so the main idea is to prove that there exists a dilatation vector field with hyperbolicity condition along the leaves. With hyperbolicity properties along the leaves, not in the, so along TF. And more precisely, let me just do a kind of, so maybe the picture is going to, let me just try. It's not easy to make this picture, but so the foliation is going to resemble to that. So we have, so I am. So what we want to do, I don't know if my picture is very good. I'm sure it is not, but I'm sorry about that. So what I want to say is that we will have, we will find a dilatation vector field so that along TF, we have a contraction. So we are going to force a contraction along the TF bundle, and we have the dilatation along the transversal bundle. So we get at the end, we are going to have to construct a dilatation vector fields that have some hyperbolicity conditions. And you see in that construction that the tangent, so the leaves, by the very construction, the leaves of the foliation F becomes the weak stable leaves of this dilatation vector field, right? And so you prove, so first of all, you prove structural stability because you know that this hyperbolic dilatation vector field is structurally stable because it is a hyperbolic and it fulfills. So of course, there are plenty of things I'm not able to speak because you have to verify a lot of things, namely some transversality questions, which are kind of delicate, but you at the end, the strategy is that we are able to prove that these dilatation vector fields having these hyperbolicity properties is structurally stable.
I'm sorry, you have only 1 minute. 1 minute, yes?
Yeah, okay. I will finish in 1 minute. And so we are able to prove the structural stability, and because the foliation F is the weak stable foliation of that dilatation vector fields, it will be also structurally stable because of this property. Because the proof is that if you take these dilatation vector fields along F, if you move F to F prime, you can move this dilatation vector field to a vector field which is tangent to F prime. Okay, this new dilatation vector fields by structural stability for vector fields, for real vector fields, is topologically conjugated to the original one, and this topological conjugacy maps the structural. So the weak stable leaves to weak stable leaves. So it provides for you the conjugacy between F and F prime. Okay, so this is the very rough idea of the proof. And I think I will stop here, and I am going to thank you again for your attention. And
thank you very much. Let us thank speaker. Yes. And then, are there any questions? Вот, Юрий Сергеевич, микрофон только включите. Ага.
I have several questions, probably rather statements, not questions. The first statement is that genericity of polynomial foliations without algebraic leaves was established in the work of Petrovsky and Landis of 50s. So I guess they went the same way as Giannolo had, and probably they did not establish such a beautiful example as Giannolo established. So this is my first remark. The second remark is about the Anosov conjecture. I am a living witness of his statement of this conjecture at the Arnold's seminar on dynamical systems, yes, in '63. And I do not think that he have ever published this conjecture. So I remember quite well how he formulated this conjecture, and I advertised this conjecture since then, but I do not think that he himself have written it anywhere. Right. And probably the third remark is that Bernd Müller, my first PhD student, got some density results without invariant line at infinity, that is without monodromy group at infinity in '75. So it is a first step which was before Loret and Rebello.
Okay.
So
you told me already. Yeah, right. I'm sorry. Yeah, you told me that. Yuli, I'm sorry. Yeah, I forgot that.
No problem. So I am very much interested by this criterion. I think it is new. Is it published already? This general criterion.
Okay, so the Giannolo part is published in Aurelien's habilitation, but
yes.
This new criterion is is being written at the moment. So I think, I hope we will have the whole paper quite soon.
Yes, it sounds very, very interesting. Thank you.
Thank you very much, Willy. Thank you for your questions and your comments.
Any other questions? There are no. Then we thanks again our speaker, and then we have how much minutes? 5 minutes before the next report. Thank you very much.
Thank you.
Витя, ты попробуешь демонстрацию этого экрана?
Да, сейчас, секунду. Значит, так. Портажили. А меня нужно этим кухостом сделать.
Вот, видишь, как вовремя вспомнили.
Сейчас сделаю. Так, только я тебя найти не могу.
Имя латиницы, если...
Да.
Так, вторая попытка. Так, кажется, это должно быть то, что нужно. Оно сейчас видно?
Да, Дима, да, ведь видно. Все хорошо.
И вроде и сейчас листается, да?
Ну, кстати, вот у предыдущего докладчика со звуком было что-то не очень, правильно? У тебя нормально все? Или только у меня так было? Или у всех?
Нет, я тоже плохо слышал. Я думаю, что это проблемы связи просто.
Ну, может, там это во всей Франции такие проблемы нет?
Нет.
Это хорошо.
Да, на всякий случай. Сколько у меня будет времени? 40 минут или 50?
Да, 40 минут? Вроде 40.
40-45 и плюс там эпсилон на
вопрос. И остальное на вопросы, да. Хорошо.
I think we can continue. And next speaker is Victor Kleptson. Pete.
Thank you very much. Thank you very much for this invitation. I'm very happy to speak, and I will be speaking on our joint work with Anton Gorodetsky that's devoted to the generalizations of Furstenberg theorem in two directions. One is adding a parameter, and second is removing the stationary. So, and before I start speaking, I want to say that I will definitely not cover all the details and so on. I'm going to show what we know about the beauty of the subject and explain what's going on. But it's definitely not a survey of a domain. There are many people with many other results. Zhitomirskaya, Arthur Avila, the famous 10 Martini problem and things around that. There are David Damanik, there are works of Ilya Goldshaid, Sasha Sodin, and recent work of Sodin and Macera. So there are many works that I will not cover in details. I will just concentrate on two parts that I chose to try to explain. So if somebody doesn't get mentioned, it's not because I am impolitely ignoring his works. It's because I don't have time to do both deep dive and essays. So all this talk will be around random matrix products. That is, there are matrices in some some k by k matrices that one can immediately assume to be of determinant one because, well, scalars commute with everything. And we have probabilities of that are associated to these matrices. And we make a random product multiplying these matrices, choosing on each step a new matrix in a random way with this probability. Then the classical question, going back to 60s, is how does such a product grow? And definitely, if tossing a coin or rolling a die is not complicated enough, one can consider an arbitrary probability measure on the space of matrices to choose matrices with respect to this measure. So we're randomly choosing a matrix, so we're making this a random product, and we're asking for its growth. Then two theorems going back to 60s are one by Furstenberg and Kesten, saying that the exponential growth, so logarithm of the norm of such a product divided by the number of factors, converges almost surely to a value that's almost surely a constant. So that's why I denote it lambda fk. And the logarithm of norm is a submultiplicative function. So such a convergence, it's just a kind of subadditive ergodic theorem that nowadays it's nothing too complicated. And on the other hand, there is another theorem due to Furstenberg saying that if the matrices, if the law for these matrices is sufficiently generic, then this growth is indeed exponential. The coefficient, the Lyapunov exponent is strictly positive. And the conditions at the time were that there is no common invariant measure on this projective space on which the matrices act, and there is no invariant finite union of proper subspaces. So, for instance, if all the matrices are orthogonal, there is no growth, but there is no but the Haar measure, the standard measure on the space of directions is invariant. On the other hand, it's not too difficult to make an example preserving both horizontal and vertical plane, horizontal vertical direction on the plane, where also the there is no exponential growth by diagonal matrices. Hand-waving explanation for such a growth, I'm going quite quickly here. I think everybody knows it. So hand-waving explanation for this is that a matrix of large norm actually does expand almost all the directions and sends most direction to quite a short, quite a concentrated line. So when one multiplies two all products that are already of large norm, most probably the log of norm will be almost additive. It's difficult not to expand. Well, it's a hand-waving explanation, but I'm not going to enter into more details. So the main question with which the first part of our study started is what happens if we add a parameter to this setting. That is, instead of considering a random matrix, we consider a random matrix depending on a parameter. So elements of matrices are now not anymore numbers, but functions. And parameter, say, belongs in an interval J, an interval on the real line. So the same then happens for the product. It's a product that depends not only on the randomness, but also on the parameter. And if we fix an individual value of the parameter, then it says if we substitute this value of a parameter, we are back to case one to the classical Furstenberg theorem. And for individual A, almost surely one gets convergence to some exponential growth with some exponent depending on this parameter. But interesting question is the other way around. One first fixes a randomness, and for a randomness fixed, one gets a product depending on a parameter, so its norm is a function of the parameter, and the question is how does it behave, what could be done. And I'm going to do some quick simulations. That's nothing too much complicated. One can redo the same in any programming language. I'm taking a diagonal matrix that has a decent expansion, 3 times in one direction. I'm taking a rotation by an angle that will be a parameter, and the 3 matrices between which we choose are diagonal, diagonal post-composed with one this rotation, and diagonal post-composed with rotation by a double angle. There is no deep idea for this choice of matrices. That's I guess if one does any other choice, that would be same kind of risk. So let's take these 3 matrices and let's take a product of some decent length, say 30, and let's consider how a log of the norm of that product varies with the parameter. So on this graph, a red line is a graph of theoretical lambda depending on A. So for each A, the value that we would get almost surely in the limit. 30 is not infinity. 30 is a finite number. So that's nothing too much surprising that the values we are getting differ from the limit. But no, that's not this part that's highly important. What is important are these small gaps, small backs, small descents. If we do another simulation, so same matrices, same length of product, we we redo the sampling. So again, 30 times a die is thrown. A new product is taken its logarithm and divided by n. And again, that seems to be time to time close to this limit curve, but with these descents. And again, I'm just describing what we see. We are not yet doing any conclusions. And what I'm going to do now is to do 2 more steps of numerical simulations, and then pass to the description, to the mathematical theorems. So now we are doing a product of length 100, same matrices, so same curve that would be theoretical limit for any individual parameter. And again, we see the curves, the sampled curves go closer to it, and time to time descent. We are doing 1 more simulation. We're getting again a curve that's close, but time to time descents. But now let's do a clever thing. At every such descent, abrupt descent of the graph, let's magnify, and let's do this. Let's do this sampling, because, well, when one constructs a graph numerically, one uses finite set of values. A equals 0.5, A equals 0.501, 0.502, and so on. So say 1,000 individual points on the parameter x. So now, whenever the graph starts descending, let's refine the partition around this point. And here is what we see. It turns out that each of these gaps, each of these abrupt drops, actually went much deeper down, but at first computer did not notice it, because it does so in a very, very thin, exponentially thin window. And if we're taking 2 points, one to the left and one to the right of such a small exponential descent, we do not see all this descent. And that's, for the moment, are just purely simulations. I will present theorems that give a proof for that, but before doing that, I wanted to ask if it's clear what we see, and if anyone has questions just right now. Okay.
Victor,
yes.
I have one question. So do you know experimentally how thin you have to go to see this?
Well, I know it theoretically. Actually, because I knew what should be done from theoretical point of view, I programmed quite a deep search. So actually, the deeper you want this part to descend, the smaller is the exponential part of the window. So the procedure should be as follows. For instance, you refine 10 times, and if you got something noticeably deeper than you got on the previous step, you refine again, and you repeat until you stop getting something interesting.
Okay.
So that's it. And now let's pass to the description. So what's happening? Imagine that you have quite a long product, so a product of length 100 or 1,000. And this product, as I said, depends on the parameter. And imagine that around some parameter value, this product can be decomposed into 2 parts. First, 30%, or say first 100. Sorry, out of first 100, first 70 and last 30. While we are varying the parameter a bit, the first part almost does not change. It still contracts. It still behaves, in a sense, in a hyperbolic way, contracting everything from one direction and expanding in the another. The same happens for the second part, for the last 30 maps. But at some intermediate parameter value, when we vary the parameter a bit, the point, the direction where the first part expands everything becomes exactly the direction where the second part contracts everything. It's a very, very thin part. It's, because as we've seen, a large norm matrix does a good expansion almost everywhere. But aside of this, there is small part where it's the fullmost contraction, and there might be, and actually under reasonable assumptions, there will be a smaller window where the first part have expanded everything. That's exactly where second part collapses everything. And so that's what we see here on this descent. It's what the first part made expanded, the second part contracted. So these two parts of the project started working against each other, and that's why we see a huge drop in Lyapunov exponent in log of the norm divided by the number of factors. So that's the description. And this theorem that we proved is that, sorry, I'm going to say them in the other direction. So this theorem that we proved with Anton Gorodetsky is that indeed under some reasonable assumptions, that's what we observe with high probability. So when we are making a statement in a probability setting, there are two different kinds of statements. There are statements for infinite number of, for n tending to infinity, and that's usually an almost sure statement. And there is a finite statement, what happens for finite n. But when making a statement for a given finite n, one should be careful because there is never an almost sure statement for a finite number of factors, because, well, we cannot forbid a fair coin to give us 30 or 40 or 50 heads or tails in a row. That's quite improbable to have 40 tails in 40 samples, but that's not probability zero. So the statement is that with high probability, that's indeed what we see, that there are some very small of exponentially small in fourth power root of n. So that's, well, that's still quite small. There are some number of very small intervals in the parameter, along which such that on this outside these parameter values, the product does expansion as it should uniformly with with error at most epsilon for every given epsilon, and on each of these exponentially small in square root of n, in fourth power root of n, sorry, in each of these very small parameter intervals, one can divide the product into first part and last part, such that what happens first behaves hyperbolically, expanding in one direction with a prescribed strength, contracting in the other. The same holds for the second part, and these two parts work against each other. So before this small window starts, even though there is a small angle, they still almost help each other. That the closer image of almost all the vectors comes to the contracted direction for the other part, the more these two parts cancel each other. And when we are done, when we jump over it, we again get to the almost full norm. So that's exactly what we have seen on this graph. The product behaves close to the limit value, except for sometimes in a very thin part, there is a rapid drop and rapid increase, and we're back on track. So that was a finite end statement. And passing to the limit from for the infinite case, for what happens in the limit as n tends to infinity, one gets the following. On one hand, almost surely, when working with upper limit for the Lyapunov exponent, one gets this predicted value function, the red one, the Furstenberg-Keston exponent for each parameter. For every parameter, one gets such an upper limit. However, almost surely there is a random residual G delta dense subset of the parameter interval on which a lower limit not only is different from the upper limit, but vanishes. So contrary to the classical Furstenberg-Keston theorem, one cannot anymore say that for every a, the limit 1 over n logarithm blah, blah, blah exists. It's not true that almost surely the limit exists for all a. There is a set where a lower limit is as small as it could be, it's just 0. And finally, well, it's topologically big set, it's a G delta dense, because these cancellations under our assumptions can happen everywhere, so they would happen everywhere. And that's very natural that it's topologically dense for the standard arguments. But as all these cancellation windows are very thin, this set is not only of measure 0, but it's of 0 Hausdorff dimension. And well, here are the assumptions for our result. First of all, we ask individual condition for individual Furstenberg condition for every parameter value. We ask uniform boundedness as matrices depending on a parameter, and ask uniform boundedness in C1 norm, which is a bit technical because, well, if we needed, we could handle some unboundedness, replace it with moments, but it's already quite complicated technically. So we chose first to do the simplest possible thing that's already, in my opinion, is quite interesting. We ask that at no parameter value there is a uniform hyperbolicity, in a sense that there is no finite union of cones that is sent inside itself by all the matrices. Like if, for instance, we forbid that all the matrices have positive elements, because then the positive cone would be invariant. And a final assumption that uses, sorry, I perhaps should have underlined it earlier, our theorems work we're working in dimension 2 for SL2R. So the last assumption uses direction in a non-trivial, uses dimension 2 in a non-trivial way. We're asking that everything spins in the same direction as for any non-zero vector and any parameter and any of the matrices we work with. As we increase the parameter, the image of the vector spins in the positive direction with a speed that's bounded away from zero. So these are two theorems for the parameter-dependent Furstenberg theorem. And perhaps one last thing I wanted to say here is just in one or two words, an idea of proof. The problem is that we want to work uniformly in the parameter, and the statement is not so evident to state as uniform in the parameter. So, for instance, one can pick any finite set of parameters and ask for the Furstenberg theorem to be the conditions to be held simultaneously, or working for these parameter values for a finite set for a finite, and if there are not too much parameter values chosen, then if probability of failing for each of them is sufficiently small, it's still okay for all of them, but it's working with finite parameter values, as it's not clear how to jump to parameter dependent version. So the answer is twofold. On the one hand, one key idea is the distortion control that I guess most of the speakers know, most of the participants have met and used many times. And the other is the description of what happens if we take image of a given vector under a long product and ask how does it turn, how does it spin, what can be said about the argument of its image as we change the parameter. And the answer is as follows. When we get back here, we notice that the image of the initial vector v0 makes a half turn in the plane exactly at the moment when we pass through a window. So considering these arguments, these functions, as a function of number of iterations and parameter, tells us where do these windows happen to occur. They occur when we see half turns or full turns if instead of considering points on the plane, we consider projectivization, because then two opposite vectors correspond to the same point on the projective line. So that's this way of detecting cancellation, these windows, that's exactly what one needs to start speaking mathematically, start saying what should be we be looking for. And from this point, the rest of the proof unrolls very naturally. If it does not occur, we control the behavior by distortion control, and the number of windows that can occur is quite easily bounded, because one cannot have too many turns for too many jumps for a monotonous function. So that's it. So I'm not going to go into more details because I'm halfway through my slides and and I've elapsed 3/4 of my time. But I want to say that once this is understood, everything is really nice and doable. I will perhaps almost jump over this by saying that one of the key motivations for this is that product of random matrices depending on a parameter that's what naturally occurs in dynamical approach for one-dimensional Anderson localization. So when writing a discrete Schrödinger equation with a random potential and looking for its eigenvalues, the fact that any randomness, any non-trivial randomness leads to the localization, that is to the presence of eigenfunctions, that's seen on the looking for eigenfunctions leads to a recurrent equation that becomes a product of matrices depending on energy or on the conjectural eigenvalue. So looking for eigenfunction for a randomly perturbed Schrödinger equation, that's exactly and it's really immediate translation. That's exactly translates into description, into the behavior of product of random due to the potential matrices, depending on the parameter that's energy. And it's indeed this order. First, one takes a random crystal, random defects in a crystal, or anything like that, and then perturbs it. And then for a given crystal, one is looking for an energy that generates the eigenfunction. I will perhaps jump over it because I want to speak about the second part. And again, I'm repeating that I'm not that there are works of others, and I'm not making a full survey. I'm just making one direct dive. So imagine now, and by the way, even if you didn't follow the parametric part, it's okay now to return and to listen for second part. So assume that we're in the same Furstenberg type setting of a product of random matrices. Each matrix is chosen with respect to its measure, but this measure independently, but these measures are no longer the same one. So for instance, imagine that on each prime number, we're tossing a coin to choose between A1 and A2, and on each composite number J, we're choosing the matrix rolling a die and choosing between B1, B2, B3, B4, B5, B6. So two laws, and that's not even odd. That's just some kind of a general mix. Then one can ask for the same question. Sorry, I have first jump over the conditions, or no, that's okay. So assume that we consider such a product. Then on one hand, it's completely natural to expect it to grow exponentially under some very reasonable assumptions, once one forbids some natural things that come into mind. On the other hand, doing such a study, we're completely we have all our toolbox that abruptly cease to function. Usually one uses the notion of a stationary measure, but there is no notion of a stationary measure for a non-stationary product. One is used to use Lyapunov exponent and all the product that's associated to it. No more Lyapunov exponent, and everything goes on in the same way. We're used to use all the tools that are present in for the stationarity case, but we're no longer stationary. So our goal is indeed some kind of a Furstenberg statement. And before making the statement, let's say what should we be afraid of? For instance, if we're in one of the cases already forbidden by Furstenberg's theorem, for instance, if all the matrices preserve a norm, if all the matrices are orthogonal, or anything like that, then definitely there will be no exponential growth. But even if each individual measure does not preserve anything, it might be that these measures become closer and closer and closer to something that's norm preserving. So a natural way of stating the conditions are by saying that the measures with respect to which we choose matrices in our random product belong to some compact set in the set of in the space of measures on K by K matrices. So, and now under some assumptions that I'm going to list, indeed we get a kind of exponential growth, and that's what I'm going to state, and that's our second main result with Anton Gorodetsky. And I will present two more examples of some strange behavior, and that's what I will end my talk with. So we ask all these measures to be uniformly compactly supported. We don't want to have two matrices that are too large. Again, one could imagine weakening this assumption by using some moments and so on. We didn't want to go into technical details. It's already too complicated. We want to have, for classical Furstenberg theorem, one asks that there is no measure that's preserved. When working in a non-stationary setting, it's much more natural to think of what's happening, saying that what's happening at each time is considered as a separate instance of a space. Like if it was different fibers for a skew product, and this means that instead of speaking of an invariant measure and forbidding an invariant measure on the projective space, on the space of directions, one asks that there is no measure on one of these sets that's sent to a given measure on the other by almost all the matrices. So the assumption is that for any law from our compact set of laws, there is no measures mu and mu prime on different circles, on different space of directions, not circles, projective spaces, projectivizations of RK. So there is no measures such that one of them is almost surely sent to the other by projectivization of our linear matrix. And the same applies to subspaces. There is no finite unions of proper subspaces such that one of them is almost surely sent to the other by all the matrices from by all the matrices on which our law is supported. So, as I've said, that's the assumptions under which we are working, and this no deterministic image, that's what replaces common invariant measure, for forbidding common invariant measure in the in the stationary setting. So our result in this direction is that there exists a sequence that grows, that has a lower bounded growth, such that a logarithm of norms behave like this sequence in a sense that, well, a finite n theorem is that with high probability, such a product is close to this predicted value. And in the limit, almost surely this product behaves like this sequence. And and such a statement were already also made by Ilya Goldshade. There is a very different path here. Proved that length of vectors almost surely grow exponentially, and he established some bounds on the growth. Perhaps one last thing I wanted to give here is the example that shows that for the exponential growth, that's both absence of invariant measure and no finite invariant subset set of subspaces, that both these assumptions are important. If one takes matrices that are most of the 4x4 matrices that are most of the time of this form, that we are doing something quite reasonable in first two coordinates and something reasonable in the second two coordinates, in the last two coordinates, but we multiply everything by 100 in the last two coordinates and contract everything by 100 in the first two. And very rarely, time to time, really very rarely, we toss a coin to decide if we switch the first two and the last two coordinates. Then on one hand, the norm still is quite growing, but it cannot be any more well predicted in the same way as before, saying that there is a predicted value to which the log of norm is linearly close, because it's just one tossing, if we decided to switch or not, that for a long time decides whether the first and the second parts of the product will work together with each other or will cancel each other. So we indeed need this assumption to have such a conclusion. And well, I'm perhaps jumping over that to say that there are very nice applications of these two non-stationary Schrödinger operators, and there are many open questions, and there are many directions for open problems, and there are many people working on it. So that's everything I wanted to say, and thank you very much for your attention. Are there any questions?
Thank you very much. Let's thank speaker. And then are there any questions? What? Please, Katrin.
Yes, thank you, Vito. Very nice talk, very nice results. I have a question about the first part. So you have results about the lim-inf, the lower Lyapunov exponent being 0 for some applications. Is this important for the applications, for example, with the Schrödinger co-cycles, these type of results?
Well, it is important. Let me think. I would say that that when you notice this cancellation, that's what describes to you dynamically why there is exponentially localized eigenfunction. It's because when you consider such a cancellation window, so take not the full Schrödinger cycle, but the product from say -100 to 100 term, and imagine that there is some parameter, some intermediate energy, some intermediate parameter where you observe a cancellation. The first part works against the second part. Then if you add 100 more factors in the beginning and 100 more factors in the end, the cancellation will still be present in this window because you still observe that, well, more or less speaking, whatever was before went to all the same point somewhere here, and during this window it went through the contracted part that's described by a longer part afterwards. But now these are a longer products, so one knows better for them, so one finds better smaller window and better energy value, and going like that, one actually finds the energy at which energy and a vector that's in the middle that's contracted both in future and in the past. So knowing about this cancellation, that's what tells you, that's a dynamical point of view on the existence of exponentially decreasing eigenfunctions that are no longer generalized but true. As for if this G delta set, if this lower limit is really applied, I would not say so. To me, I would say that it's more this understanding that helps.
Mm-hmm. Okay, thank you. Thanks, Ma. Thanks a lot.
Thank you for your question.
Are there any other questions? There are no. Then let's thank speaker again. And then we have 13 minutes.
Yes, so we have a 13 minutes break. And
thank you very much.
Oh, and I should stop sharing my screen.
Hello, everyone. Can you hear me?
Hello, Ilya. Yes.
Yes.
Great.
Okay.
I'm very glad to hear you. Yes. I guess. Yeah.
I'm going to share my screen. Give me a second. Let's do it this way.
It looks that you started the share screen, but I'm yet getting on.
Yeah. Give me a second. I need to set up airplane, and there are like 100 different devices here.
Oh.
But I'll figure it out. I have a plan B if it doesn't work. Okay. Oh, okay, maybe I should do this. Oh. No.
No.
Okay. Okay, plan C. Okay, let me try once again.
Mm-hmm.
This way. Oh, great. It works. It works through cable. That's excellent. Okay, can I put like this just in case? Okay, that's very good.
Okay. Then, if everybody is ready, let's start. And it's my great pleasure to pass the word to Ilya Kachkovsky for his talk on quasi-periodic operators with monotone potentials.
Okay, thanks very much. I'm really glad to be here. Thanks for your kind invitation. I wish I could be there in person, but maybe some other time. Yeah, so just some clarification that MSU is Michigan State University, not Moscow State University. Okay, and I will be talking about quasi-periodic operators with monotone potentials. I'll be using slides that I already wrote. I hope you can see them, and sometimes I will write something on top of them or make corrections if I find any mistakes. Okay, so what is a quasi-periodic operator? We consider operators acting on L2 of ZD, so operators acting on integer lattice, d-dimensional integer lattice in the space L2, so it's a Hilbert space. And in general, an example of quasi-periodic operator would be the following family of operators. You have the discrete Laplacian. Okay, so let me just remind you what discrete Laplacian is, just in case. Delta psi n equals sum m minus n equals 1 psi of m. So the result of applying discrete Laplacian to vector psi on a lattice is the sum of the values of the function at all its neighbors. This is the L1 node. Okay, so it's a discrete Laplacian plus the operator of multiplication by potential. So it's a Schrödinger operator, and the potential is a quasi-periodic function. So what it means is that we take some function f, which is originally one periodic, f of x plus 1 equals f of x, and then take its values in the dimension 1 just over the trajectory of irrational rotation. In general, we take its values at the points lattice vector inner product with some frequency vector, where the components of the frequency vector are assumed to be rational independent over integers, and x is some initial phase. Usually it's convenient to consider quasi-periodic operators as operator families, depending on the initial phase of the irrational rotation or whatever the higher dimension analog is on ZD. And they satisfy some nice covariance properties. So for example, if you replace x by x plus n omega, let's say m omega, then the whole operator is just going to translate by the vector m. So the translation in lattice is a unitary equivalence, so it's going to become a unitary equivalent operator. I will not talk much about ergodic Schrödinger operators in general. I'm actually going to be talking about something more simple. And we will be talking about a special class of such operators, operators with monotone potentials. So the function f will satisfy the following properties. It's something that we call Maryland type, based on the classical Maryland model. So we assume that f is unbounded. It goes from minus infinity to infinity on the interval 0, 1, then extended by 1 periodicity, and satisfies this Lipschitz monotonicity condition. In the main result, there will be some extra technical conditions which I will not even mention. But for example, if you take a function sufficiently smooth and doesn't behave very badly on plus infinity, then the results will work. Okay, so, and as usual in quasi-periodic operators, for many questions, we assume that the frequency vector is not very close to rational vector. So we will assume a Diophantine condition that the distance from n omega inner product to the integers is bounded from below by some power of the vector n. Well, so technically you have to assume here that n is not 0, otherwise the right-hand side is not well defined. Okay, we will consider these operators in the regime of small epsilon. And we want to know about the spectra of such operators. Well, okay, our final goal is just to diagonalize this operator, to find the basis of eigenvalues and eigenvectors. And there are many ways of proving. Well, so as a consequence, we want to show that this operator has purely point spectrum. We want to construct nice decaying eigenvectors. In general, there are many ways to prove that operators have point spectrum. So this is one of the methods which is, in a way, the most explicit one. All right, so some general results about monotone operators. Yeah, by the way, feel free to interrupt me if I'm going too fast or if something is unclear. Yeah, anyway. There are a lot of results about potentials with analytic functions f. There will be, I assume, several speakers who will be talking about different cases. Monotone case is a little bit different, and in a way, it's easier. And it's also been studied in several different works. So let me give some quick overview without exact references. Okay, the most famous example of a monotone quasi-periodic operator is the Maryland model. Maryland model is the case where this function has a very explicit form, just tangent phi x. And it is known by the works of many people, this is the most recent one, Zhytomyrsky and Leo, that these operators have purely point spectrum. So it was kind of one of the first examples of quasi-periodic operators where you can prove
Anderson localization explicitly, and in some sense, because of this function is a tangent, it's sort of a complete integrable system in a way. So there are some things which can be calculated, some things for this system, like the Lyapunov exponent and integrated density of states, that can be calculated explicitly because of the particular shape of the function. And one of the natural questions would be, what can you do if you replace tangent by some general function with similar monotonicity properties? And there are two previous results. So one of them, okay, so if you talk about chronological order, that there is a result by Belissard, Lima, and Scoppola. They showed that if the frequency is de Fontaine and epsilon is very small, depending on de Fontaine parameters of the frequency, then these operators, so the function f also assumed to be analytic. So basically, it's a restriction of a meromorphic function, one periodic to the real line. And for small epsilon, they showed that these operators have Anderson localization, and the proof was based on some KM type iterations, which I will mention in the end. So I will explain a little bit the relation of our method with KM method. In case d equals 1, there are much more precise results obtained. So by my work and my work with Zhytomyrskaya, so we know that if dimension equals to 1, so the lattice is just the integers, then the operators have purely point spectrum for all values of the coupling constant, not just for small. So it's a non-perturbative result. There are some special things that it's only true for almost every x, depending on the regime. And also there is no explicit description of the eigenvectors, but in dimension 1, much more powerful methods are available. We will focus on higher dimensions, and we will focus on the same regime as Belissard, Lima, and Scoppola, but we will do it in a much more naive way, which surprisingly will still work. So in a way, we will just try to, okay, let me scroll up a little bit the definition of the operator. We'll try to write down more or less explicitly what the eigenfunctions of this operator would be in some asymptotic regime. And then it will turn out that for a large class of functions f, the series that we write, which are formal series, actually will converge due to some cancellations. So this will provide a diagonalization of this operator in terms of some explicit power series in the variable epsilon, which have some combinatorial structure. Okay, so we need some work to make this more clear. And also I will discuss some generalizations of this result where the function f is allowed to have a flat piece, in which case the regional method doesn't work, but the modification works. Okay, so this was kind of an introduction of what is going to happen. So in other words, we will try to sort of more or less explicitly diagonalize this family of operators. Okay, and to do it, I will talk a little bit about Rayleigh-Schrödinger perturbation series, which probably is known under many other names, but in this context, it referred to Rayleigh-Schrödinger. Okay, and yeah, I said I'm going to focus on the higher dimensional case, but actually, for most of the calculation, I'm still going to do in 1D, and you'll have to take my word that this particular method has a straightforward extension to higher dimensions. So mainly for this method, the problem is notation. There are other things which are very different between 1 and higher dimension, but this is not one of them. Okay, so let's consider an operator on the lattice, L2 of 0, L2 of ZD, of the form V plus epsilon times delta, where V is a multiplication operator and delta is a discrete Laplace operator, whose definition I wrote somewhere else, and I will remind you actually relatively soon. And the important property, okay, so we will construct some kind of a formal series for eigenvalues and eigenvectors. And the important property for the formal series to be even, for the formal series to even exist would be the following, that something that we call algebraic non-resonant condition, that all values of the potential are different. The reason is that we will have a lot of small denominators, which will be Vn minus Vm, and we can treat small denominators, but we cannot treat zero denominators. So that's why we want this condition. And if in the case of a flat piece, which I will mention in the end if I have time, this condition is not satisfied, but there is a way around it. Okay, what are we gonna do? We will construct an asymptotic series for eigenvalues and eigenvectors of these operators. And there will be a family of eigenvectors, with an eigenvector attached to each lattice point. That's how eventually we'll get a complete system. And these formulas work in general case, but because of our quasi-periodic condition, I will focus on the eigenvector that's concentrated at the origin, and then by some covariance, you can extend it to any lattice point. So let's solve the, well, okay, so yeah, before going to the origin, I kind of wrote what I was gonna say. So if you have epsilon equal to 0, then this operator has a very obvious system of eigenvalues and eigenvectors, just the standard basis, the values of the potential. And we want to perturb each of them to an actual eigenvector for epsilon that's not equal to 0. And as I said, let's restrict ourselves to the lattice point of the origin. And let's also shift the potential so that the value of the potential is actually 0. So our unperturbed by eigenvector is E0, the standard basis vector on ZD, and unperturbed eigenvalue is 0. And what are we going to do? We're going to just write down both an eigenvalue and an eigenvector as a power series in epsilon with coefficients that do not depend on epsilon, and try to solve the eigenvalue equation in each order separately. In general, the solution is not unique. For example, because you can choose different normalization for eigenvector. And sometimes it's natural to normalize it in L2. For our purposes, actually, it's easier to normalize it in a way that the first component, the component corresponds to the origin, is equal to 1. It's almost the same as L2, up to perturbation of order epsilon. Yeah, so this is going to be our normalization. The zeroth component of the eigenvector is E0. The unperturbed energy is 0 because of our choice of the potential. And all the corrections to the eigenvector will be vanishing at the origin. So, and the solutions to the equations at each order of epsilon, to write them, it's going to be convenient to use the formal partial inverse of the operator V. In general, V is the operator of multiplication by the sequence Vn, which is a quasi-periodic sequence somewhere, but here we don't use it. And the inverse operator, well, this operator is not invertible because one of the entries is 0, but we kind of formally invert it on the orthogonal complement. So J is not equal to 0 here. And just extend it by 0 into the origin. So I think it's called the more Penrose inverse of V, and it will be convenient to write down some objects in terms of this operator. Okay, let's solve these equations. I'm reminding the original equations here. Let's first look at the 0 order in epsilon. In 0 order, there's nothing interesting. We just get the unperturbed eigenvector. Okay, so now let's look at the first order. The first order, epsilon to the power 1. Left-hand side, we always have two terms, Laplace and the potential. So Laplace, they will be acting on corresponding components, corresponding terms of the perturbation theory for the vector psi. Now let me just check. Yeah, I'm going to open my chat just in case if I have any messages. Okay, so and we solve this equation basically by a sequence of actions. First, yeah, this is a question on vectors, on the lattice, psi0, psi1 vectors, and we solve in 2 steps. So first we project onto the 0 component. We find something, then we project on the orthogonal component where we can invert the operator v. So let's first project this equation on the 0 component. What do we get? Well, psi0 is just the 0 basis vector. If I apply Laplacian, it will spread out this vector into the neighbors and will kill the 0 entry. So delta psi0 has no component at the origin. V psi1 also has no component at the origin because psi1 is orthogonal to psi0 and v is a multiplication operator. So the left-hand side has no 0 component at the origin. And therefore, yeah, in the right-hand side, we have E1 and E0. We know that E0 is equal to 0, so it disappears. And psi0 only has component at the origin, which means that E1 is equal to 0. Okay, and now that we know that E1 is equal to 0, we can plug it into the equation and now consider projection on the orthogonal complement of the origin. So then we have this equation becomes just like this. So E1 psi0 disappeared. We move to V in the left-hand side and everything is on the right-hand side, and we can invert V. So we get psi1 equal to negative V inverse, where this is our inverse operator applied to delta psi0. Okay. In general, remember, maybe it's useful to remember if you want to recognize perturbation theory from some other problems that you've seen, that we have shifted the potential to be 0 at the origin. In general, these denominators are supposed to look like this: V0 minus Vj, where V0 is the value of the potential at. So we already have some kind of small, well, we have some kind of denominators, not necessarily small. Right now, this is the eigenvector. Okay. Now let's do one more order, and then let's try to describe something more general. So let's do second order. Second order, left-hand side is the same, just psi1, psi2 instead of psi0 and psi1. And the right-hand side, we get 3 terms. So we know that E0 and E1 disappear. In general, we'll have E0 disappear, and all even energies also gonna disappear. So, but we'll still have, so energy corrections happen only in even powers of epsilon. Okay, but then let's solve it. Again, we have this equation now. We project it into the origin. So from that, we immediately find the second correction to the energy, which is gonna be like this. And again, some people might recognize formulas from perturbation theory. And the second correction to the eigenvector would be if we project this equation now into the orthogonal complement. Yes, so basically we get V inverse delta psi1. And remember that, okay, so psi1, if you remember the previous solution, it's supported at -1 and 1. After we apply delta, it will spread out again. It will spread into -2, 2, and the origin. But V inverse, by our definition, actually kills the component at the origin. So we only get E-2 and E2. So, and then here already you can see some kind of a pattern that
Sorry, so yeah. In a way, that's what's happening is that on each new power of epsilon, there is a Laplacian that makes propagate for the function, except for the origin that where the energies occur.
Yes, pretty much. So this is going to be on the next slide. This is kind of the well no, but it's actually good. It means you're following. I mean, anyway, so it will be the next slide, but it's not. It's sort of the main contribution to the eigenvector, but there will be other contributions. So you kind of guessed the so-called simple loop, what we call simple loop term, but there are other terms which appear only if you look at higher corrections. Okay, so but yes, so basically the general pattern in a way is that it propagates with a Laplacian in all possible directions, and each time the propagation happens, we get a factor. So because we always apply Laplacian together with this V inverse. So each time we apply Laplacian, we get a denominator. Okay, so basically you can do it in all steps, like one by one. So we start from E0, psi 0, which we know. We figure out E1 like we did. From E1, we figure out psi 1. Then we do second step, we do E2. Then we do psi 2, and so on. So in this sequence, if you have algebraic non-resonant condition, then we always have a solution. Let's write down the general term. So again, this is the equation. I'm sorry, it's a little bit too small, but it's just a reminder. Maybe I can blow it up a little bit. Okay, so and this is something that I mentioned, that in odd terms we'll get 0 corrections to the energy. So let's write down what happens in the term epsilon to the power n. So this is what we have. As I said, left-hand side always has 2 terms. Right-hand side has many terms. And from this, first, we can immediately find En if we know psi n minus 1. So from the eigenvector in the previous step, you immediately get eigenvalue on the next step. It's just delta psi minus 1 is 0. So basically what happens is that we propagate eigenvector by the Laplacian and collect everything that returns to the origin. And we will kill it in the eigenvector term. Now, what happens in the eigenvector term? So we need to project it onto the E0 perpendicular. Remember that we don't lose any information of psi n here because psi n is orthogonal to E0. So so what do? We move this delta to the right-hand side and divide by V, apply V inverse. And this is what we get. Psi n is this expression in terms of the previous terms of the perturbation theory. Now, to the point that Victor mentioned, let's first pretend that we only have the first term and forget for a moment about the additional terms. Yeah, so the slides are organized in a way that there are some spoilers. Well, not many actually. Okay, so let's pretend that we only have this term. Then what's going to happen and how to calculate n correction to the energy? Basically, we have to, because we have this delta applied to psi minus 1, and psi minus 1 itself is obtained by this procedure. So to get psi n, if we look in the terms of simple loop, then it's going to be basically V inverse delta psi minus 1. Then if we do recursion step again, we get 2 factors of V inverse and 2 deltas. And so eventually, we want to calculate the eigenvalue. And so basically, we start from the origin. We travel along the lattice because we have iterations of Laplacian delta. And each time we travel, we have a factor which is like -1 over the potential measured at the corresponding point. And we have to come back to the origin. When we measure the eigenvalue, we return to the origin. This is illustrated by this formula. So the contributions to the eigenvalue, if we ignore these extra terms, will be just will correspond basically to simple paths that start and end at the origin. They do one step on the lattice each time, and the total length of the path is equal to the order in which we're considering this correction. So this is an example. This is a correction of epsilon to the power 8. So we have to have 8 steps, start from the origin, end at the origin. So this path basically starts at origin, goes to 1, 2, 3, 4, 3, 2, 1, 0. So it goes to 4 and comes back. And the contribution of this path can be written down like this. So each time we make a step, we multiply by negative inverse. There are the number of factors is one less than the order of perturbation. So there are 7 factors here. All factors appear twice because we visited the corresponding point twice, except for the very last one, because we visited kind of once. And graphically, yes, I already referred to this graph several times, but I haven't formally defined it. Graphically, these terms, when we only consider the first recursive term each time, correspond to so-called simple loops. So simple loop is, I won't give a formal definition, but it's something like this. And to each loop, we associate a term in the perturbation theory calculated in the following way. So each edge corresponds to the action of the Laplace operator because we jump, and the Laplace operator originally, if you go back to the definitions, comes with the weight epsilon. So it kind of gives you 1 epsilon. Yeah, so here it epsilon to that is factored out, so we don't see it in the equation, but you can also say that number of edges is the order of perturbation theory in which this term appears. And each vertex, each non-zero vertex corresponds to multiplying by the potential factor, by denominator, which is negative Vn to the -1, where Vn is the vertex at which we are located at the moment. Okay, so then we have to consider all simple loops. On one-dimensional lattice is a relatively simple picture, but on high dimension, we have to consider all paths that starts and end at the origin. They can be complicated, they can travel same point multiple times and so on. Okay, now, what happens if we no longer forget about these terms? So this is something that we can illustrate by attached loops. In particular, suppose that, yeah, so we call this attachment terms. The language will be clear in a moment. And suppose for a moment that when we expand this recursion, each time we use this rule, but once we use one of these, then what's going to happen? Then actually, if we, instead of applying this term, we expand it using this term, well, what's going to happen is that we have an extra factor of E4, which itself has a similar expansion, but of the lower order. And we agree that in E4, we are not using this rule. So E4 is obtained by the Bain rule. So E4 is just the sum of simple loops. And yeah, so there is difference that we have. We do not have a negative factor. We have a positive factor. This factor is an extra because there is no delta. And we get again psi, but of smaller order. So in the end, let's have some illustrations. So what happens if we, yeah, so let's say we are in order 12 of the perturbation theory. We are using the simple loop rule all the time, except for one time where we use this rule in the order 4. Then what's going to happen is the following, that we'll have a product. We'll have a product of whatever we get from the simple loop rule. We'll get an extra factor, -1 over V3, which is the step on which we change the rule to this one. And we get the factor E4. And we agree that in E4, we only have simple loops. So this is one of the examples of simple loops in E4. In general, how does this work graphically? Well, graphically, we can say the following, that we not only we can consider simple loops, but whenever we apply the other rule, we can attach attach another loop to our loop. So we choose a point where we change the rule. Then we have an additional loop which corresponds to this E factor. And you can introduce a special attachment factor which will correspond to the extra V inverse here. So graphically, if we have a diagram like this, so this part of the diagram gives a contribution of Vn inverse. So we get an extra denominator, but without a negative. Okay, so this is just an example of one term. In general, now we can formulate by hand waving a little bit that the general perturbation series is you have to consider all diagrams like this, where you're allowed to take simple loops. You're allowed to attach additional loops at any non-zero point, and then you can repeat this process. So each term in the perturbation theory, well, so the contribution to epsilon to the n in perturbation theory has a huge amount of terms. Each term can be represented by a diagram. The diagram is a collection of simple loops attached to each other using these rules. The total number of edges in each loop has to be equal, in each diagram has to be equal to the order of perturbations. So this one corresponds to order 12. It's basically 8 plus 4. Yeah, this one doesn't count, but this one counts. So yeah, it's yes, so sort of the order of perturbation theory is the number of edges which are actually generated by Laplace operator. So these are edges which are marked with arrows here. These ones are by Laplacian, this one by Laplacian, but this one corresponds to the attachment factor which doesn't have a Laplacian in front of it, so it doesn't give you an extra epsilon. It still gives you an extra denominator. But the total number of denominators will still be one less than the number of edges, because we have an extra denominator here, but on this loop, this point does not have a denominator. So the number of denominators is still the same. And to illustrate it, we have a sort of a tree of loops. There is like the base loop, which ultimately comes back to the origin, and you can have a lot of loops attached to each other. So this stuff is not new. So maybe the description in terms of loops is relatively new, but this series have been considered in many papers, including math and physics papers. So in particular, there's a paper by Arnold where he does, yeah, this is probably the closest to this form that we've seen. He was looking at gaps at continuous Métis operator. Okay, so I have constructed a very complicated series. And I promised to explain you why it converges for our case. So let's talk about that.
Yeah, and I'm sorry, just to remind that there is theoretically 6 minutes left. Well, plus perhaps some time of questions, but be advised that 40 minutes.
Okay, so yeah, I'll kind of give quick things. Yeah.
I guess we can play a bit.
Well, I thought it was 45, but okay. Yeah, I mean, whenever required, I'll watch the clock and I'll wrap it up whenever needed. Okay, so let's talk a little bit about convergence. So let me illustrate the main difficulty and a sort of a solution to this difficulty. So it will be more like a little bit more like hand waving, but I hope you'll get the idea. So remember that we replaced Vn by 0 to simplify the computation. But suppose that we don't do it and apply this procedure at each Vn, because we ultimately need to do it to construct the basis of eigenvectors. Now the denominators that we're going to get are of the form 1 over Vn minus Vm. And remember that Vn is obtained by taking x plus n omega. Right? And eventually, there is no way to avoid it. Sometime we will get n omega close to m omega. And as a consequence, we can get small denominators. Yeah, by the way, so this is something I wanted to remark, is that if Vn was an isolated value of the potential, then the series would converge. It's just a standard perturbation theory thing. But in our case, it's not isolated. It's a dense sequence in the end, because it's the f of x plus n omega. So as I said, we inevitably get small denominators. And this is where we get trouble. So suppose that we have some n prime, which is very close to Vn. Vn is the initial point of the perturbation. Okay, so then we can produce individual terms of the series which will explode. Because what we can do is just consider a simple loop. So we start with n, because we started Vn. We go to n prime. So then we get the denominator Vn minus Vn prime. And then we can do a lot of very small steps. Each time we get a step, we come back to the point n prime. And each time we do that, we get a small denominator. We can get it as small as we want. So we can get it epsilon to the 100, and we get epsilon to the 100 each time we make a small step. And we only get epsilon squared in the numerator because the length of the step is 2. So this thing is going to explode. And the idea is that there are other terms, and we can try to cancel it. So this is a simple loop term. And actually, we can cancel it with the corresponding attachment term. So instead of taking a simple loop that makes one extra step, we do the attachment procedure. So that's we do an attached loop, and turns out that there will be some nice cancellation, because the attachment loop will not have that absence of the minus sign is important. Yes, and then we have small denominator cancel with numerator. So let me illustrate it in the last 2 minutes on. Yeah, so this is just some explanation of what's going to happen if we actually consider an f. I already said that. And let me demonstrate some cancellations. So suppose this is a simple loop that I mentioned. So it starts from, let's say, from the origin, it gets to the point n, goes to n plus 1, goes to n plus 1, n. So when it does this, it can create trouble. And then it turns out that you can cancel it with the following 3 attached loops. So instead of making one step here, you're attaching a loop like this using the attachment rule. And you do it with each time it comes back to a small denominator. So there are a total of 4 terms. And if you make a calculation, you know the contribution of like so-called the main path by h of x, then you can calculate the attachment terms like this. So yes, well, basically I was just applying the rules. I don't really have time to explain in detail how these terms appear, but you can just believe me that if you apply the rules I described, you're going to get exactly this. And now, what's the point? So in this particular case, you can expand it. And in the end, what do you get? You get a small denominator, which we already had, but we get something in the numerator. In the numerator, we get, because this loop, the attached loop started like this, we have this thing, which is also small, right? So we get f of x minus f of x plus n omega. We get f of x plus omega minus f of x plus n plus 1 omega. And here, the difference of the arguments is also of the order n omega. And roughly, that means that the numerator will create a cancellation. And then basically this, in a way that the smaller the denominators are, the better the situation is, because the more precise the cancellation will be. Okay, so and then the idea is that you do it like, there are, as I said, there is actually a tree of loops. So there is a big chain of cancellations. So there is some work that needs to be done, but it's possible for the class of operators I considered, it's possible to do it. So, and then the perturbation series will converge, and you get eigenvalues and eigenvectors that diagonalize the operator. So Yeah, okay, so that's kind of the conclusion. So because of presence of attached loops, you can combine certain best situations with corresponding situations with attached loops and create small numerators which will cancel small denominators, and eventually you will obtain convergence. So maybe it's a good place to stop. So this is kind of the idea of the main result.
Thank you very much for your talk. I suggest that we all thank you. And I'm using this opportunity to ask a question myself. And so this place where you've stopped the talk, you've written the perturbation terms, and they turned out to be groupable together so that to provide a convergent series. Then I have a vague and philosophical question. Does it mean that there is a better point of view on the perturbation series? Does it mean that the perturbation series as it comes directly, it's perhaps a wrong angle of view, and the way how you group them is something better, that they become attached to each other for some intrinsic reason or whatever?
Yes, so actually, yeah, this is a good question. So the reason why we're interested in this is because this series is kind of the most explicit one, but I mentioned there is another approach to this problem, an earlier one based on KM theory, where you, okay, so I have a slide about it actually. So where you, instead of constructing directly eigenvelocity eigenvectors, you construct a series of unitary transformations by just this kind of procedure, and you always kill only first order terms. So, and then in this case, you kind of get these cancellations automatically, but the price to pay is that instead of explicit series, you get an iterative procedure. And there are so yeah, I mean, you probably recognize these formulas. I can give some more comments. I would give some more comments if I have time, but yes, so there are iterative procedures, different ones, which do not use cancellations, because cancellations are embedded there intrinsically, but the perturbation series gives some additional information which we will not necessarily have from these procedures. So it kind of feels nice to have a formula to get something rather than get a procedure to get something. So sorry. Yeah. So maybe one more remark is that so after we wrote the text, we found that there is another reference that Eliasson actually found something very similar. So in a completely different problem. So there were some classical papers about KM for ODs, which had, if I remember correctly, yes, again, it was some kind of a procedure to find solutions. And then eventually it was proved that these solutions are analytic in epsilon. Therefore, there is a power series for them. And then Eliasson actually found that if you analyze directly this power series and do some cancellations which look a little bit similar to ours, but different in a different context, you can also prove that they're convergent. So if you look at this paper by Eliasson, he does something very similar. He represents terms of formal series by diagrams and finds cancellations. So this is just some context also.
Yeah. Indeed, that's, yeah. Thank you very much. And are there any other questions from the audience? Are there any other questions? If not, let's thank the speaker again, and we start again in 14 minutes. Thank you. It was a really nice talk.
Thanks. Yeah, I'm sorry. I can't attend the remaining talks because we have actually an in-person seminar in 20 minutes, and I'm hosting the speaker, so I have to attend. I promise to attend the talk. Yeah, but thanks very much for the invitation. I'll try to see if I can attend other talks later.
Seminar in person makes me jealous.
Yeah.
A privilege.
It's the first one in the semester actually, so it's kind of a big deal for me.
Good luck and thank you.
Right. Thanks everyone.
Okay, so in 13 minutes.
Hi, Christian.
Hi. Who is speaking? I don't see who is speaking. Sorry.
This is Andrei.
Oh, yes. Hello, Andrei.
Hi, Christian. This is Victor.
Hello, Victor. Salut.
Salut, ça va?
Ça va? Hello, Slava.
Hi, Christian. I am glad to see you. Good evening. Dmitry Викторович. Christian, could you send me your presentation? It's beautiful. I will be appreciate to you. Okay, thank you very much. Okay, I like these things. Good talk. Good photo.
Where is this photo?
Dubna. It's the main. It's the lecture hall for summer school contemporary mathematics in Dubna. That's I recognize quite clearly. Actually, I guess if you magnify the badge Dmitry Viktorovich is wearing, that's one of the badges I recognize very well. It will have a flower of oak, which is dub in Russian. So the Dubna is a town that's famous for its physicists, and yeah, it might. Yeah, that's one of the courses he was giving me there. Let me try to find which.
It's for this conference for young.
Yes, I'm
maybe for school.
Last 2 years of high school and first 2 years of university.
Okay, okay.
Okay, I guess it's 7 p.m. Moscow time, so
yes, yes.
It's perhaps a moment to restart. So, Andrei, am I right that it's you who are showing now the slide? It's from your talk, yes?
Yeah.
No. Then whoever is, I guess you will be sharing your screen. Yes, you will.
Yeah. I'm good. I'm sharing my screen. Yeah, Victor, it's okay.
Oh, okay. You're sharing your screen. Okay. Then, so for the slide, Alexei, if
yes.
If it's you who are sharing the screen.
No. It's Andrei's slides.
It's Andrei's screen. Okay. Oh, sorry. Then we are ready to start, and it's my great pleasure to pass the word to Andrei Gogolev for his talk.
Thank you.
Andrei.
Yeah, thank you, Victor. Thank you very much. And thank you, the organizers, for the invitation to this memorial conference. I have met Anosov only once. That was in 2002 in this summer school that Victor just explained about. And I went to the website to look for pictures. And unfortunately, there are no more pictures from 2002. But this is a picture from some years later, maybe like 2005 or 2006. And in 2002, he was there, and I took a mini course from him, which was on complex variable mini course. And of course, at the time, I had no idea that I will be doing hyperbolic dynamics in the future. And I will talk about some subject related to Anosov works, which I call Anosov extension. And this is joined with Don Chen and Alena Yerchenko. So let me begin with geodesic flaws. Here is the slide of the front page of probably the most famous book of Anosov. This is his doctoral dissertation, and it says geodesic flows on closed Riemannian manifolds of negative curvature. So one of the great insights of Anosov was, of course, to recognize that these properties of horocycles on manifolds of negative curvature can be kind of abstracted into this general definition of Anosov flows. And I think, as the title of the book points out, geodesic dynamics in negative curvature was one of the major motivations for him to write the book. So let me start with just by quickly reminding about geodesic flows. But it's been a while since I used it, because now last year I was teaching using it, but now I'm teaching in person, so I'm a little bit clumsy with that. So we are going to have M Riemannian manifold. Riemannian manifold. So we fix it's a closed Riemannian manifold, no boundary. We fix a Riemannian metric, and geodesic flow is going to live on the unit tangent bundle. So this is bundle of vectors, tangent vectors, which have norm 1. And so this is your manifold. You take any vector, unit vector, that's a point in your space. It uniquely determines the geodesic gamma v of t. And you go for some t, you come to this point over here, and you take the tangent vector to the geodesic. This is your flow. So this is phi t of v. And so as I said, if all sectional curvatures of the metric are negative, then the flow is Anosov. And T is an Anosov flow. And in the book, Anosov established a number of properties. He proved ergodicity of stable ergodicity of geodesic flows and structural stability, and quite a few other results. It's a pretty long book. But my subject today would be that for the geodesic flow to be Anosov, you don't really need curvature to be negative. Namely, you can relax the condition a little bit. So we can look at this very nice space. It's a geometric space. So given a manifold, you can consider all metrics of negative curvature on the manifold. So all the geodesic flows that are Anosov, so this is going to be a subset of a bigger space, which is the space of Anosov metrics. So Anosov metric is simply a metric such that corresponding geodesic flow has the Anosov property. You can also kind of relax the geometric condition, and you can put this into the space of non-positively curved metrics. But if you relax this much, it could be that the flow is not Anosov anymore. For example, a simple thing you can do, you can consider, well, you can just take a flat torus if you want, right? Flat torus has zero curvature. The geodesic flow is not Anosov, but if you want some negative curvature and some zero curvature, you can take a flat cylinder like that, and then add some genus to it to have some negative curvature elsewhere. And the flow here is not going to be Anosov because it has this non-Anosov behavior of geodesic, periodic geodesics traveling together. So there's no good relation between these two spaces. But there is one more geometric condition which is very popular in geometry, which is absence of conjugate points. So this non-positively curved matrix, they sit inside of even bigger space of Riemannian matrix with no conjugate points. So NCP stands for no conjugate points. And turns out that this is a necessary condition for being Anosov, namely there is an inclusion like that. It's not completely trivial. Actually, I was preparing the talk yesterday and I decided I sit down and prove it by myself, but I couldn't do it right away. It's not very easy. So this is a theorem of Klingenberg, and it uses Morse theory on the space of closed curves, and there is something called Morse index formula, which calculates an index of a critical point using Jacobi fields along the geodesics. So this is a nice result, pretty old one from the 70s. I forget which year, maybe like early 70s, maybe 70. So you have these inclusions, and so what does it mean to have no conjugate points? That simply means that the obvious map, the exponential map from the tangent space of the manifold to the universal cover. So you just shoot out geodesics at a point, that's your exponential map, and this map has to be diffeomorphism. This is what it means to have no conjugate points. So it doesn't have any singularities, is a diffeomorphism. Alternatively, you can say that perpendicular Jacobi fields don't vanish at two different points. We are going to talk about it a little bit later. So this kind of Anosov metrics, which are not negatively curved, I don't think people think about them that much. But certainly there are some classification problems which are related to the subject and that no one knows how to solve. Of course, it is not as famous as, let's say, classification of Anosov diffeomorphisms problem, but I think these are interesting questions. So let me maybe advertise a couple of questions. So question one is the following. So suppose you have a metric such that the geodesic flow is Anosov. So you look at the space, so you take a manifold and you find a metric such that geodesic flow is Anosov. So the space is not empty. You've got at least one metric such that geodesic flow is Anosov. The question is, does that imply that this manifold actually has maybe a different metric of negative curvature? So if you wish, can you always deform Anosov metric by some procedure into a metric of negative curvature? I think that's very difficult. And it's true in dimension 2, of course, that's not hard, but in higher dimension, I don't think it's known. And I think it's a difficult question. I actually suspect that the answer is no, but example is very complicated. You can ask a little bit simpler question. Let me say question 1 prime. Suppose you have an Anosov metric. So same assumption, you have a manifold with the Anosov geodesic flow. Does it actually imply that the fundamental group is Gromov hyperbolic? And that I think is very, very believable, but I don't know how to approach this question. And there are other things that you can ask. For example, a well-known fact about metric of negative curvature. So if you look at the surface, so two-dimensional manifold, and you look at all metrics of negative curvature, that's homotopy equivalent to a point. It's a contractible space. That's a non-trivial theorem, but it's an old theorem. Question is, can you say exactly the same about Anosov matrix, right? So Anosov matrix is a bigger space. Can you say the same thing? I have no idea, and I don't think this is easy. So you look at all Anosov metrics on a surface, which you can kind of imagine very well what they are. Is it true that that's contractible to a point? Anyhow, so these are just some questions, and I'll start making some preparation to formulate the result. And first, I need to remind you about Anosov splitting for geodesic flows. So Anosov splitting for geodesic flows. In the meantime, any questions? So Anosov splitting in the geodesic case admits very nice description. You take a vector V, and then you take you unfold it into a curve of vectors. So you unfold it into a curve of vectors. So you have a curve of vectors like that, unit vectors. Let's say you parameterize it by some variable s. So you have V of s. So this V of s, this is a curve in the unit tangent bundle. And because it's a curve in the unit tangent bundle, this V of s is nothing else but an element of the tangent bundle of a unit tangent bundle, right? So this is an element in there. And then what you can do, you can shoot out geodesics from all these vectors, and this is what is called geodesic deformation. So you have all these geodesics, gamma, you have this canonical geodesic, gamma VT, that you're interested in, but then you have the same thing for every S. So you have gamma V, let me just call it gamma ST, and that leads to this Jacobi vector field, perpendicular Jacobi vector field. You just differentiate with respect to S. So you have Jacobi vector field J of T is just D ds of this gamma ST. So you detect how this variation, this is what is called variation vector field. Variation vector field that looks like that, and it satisfies second order differential equation. Comes from the fact that this is a geodesic deformation. So this is called a Jacobi equation. Jacobi equation is a second order equation. It reads like that: J2 prime of T. This is prime means covariant differentiation along the geodesic. And then you have your curvature tensor here. And all that's supposed to be equal to 0. This is the way you write it in any dimension. If you want, you can just think about dimension 2. When this J of T is just a function, and it becomes a familiar. It's just a second order equation like that. J2 primes T plus curvature at this point T, right? So at every point T you have a curvature. Jt equals to 0. This is in dimension 2. And once you have this Jacobi fields, you can define what does it mean. So you see how is the logic. You had this V in unit tangent bundle, and to V you associate this Jacobi vector field. So you associate Jt, what is called perpendicular Jacobi vector field, perpendicular Jacobi vector field along this geodesic, and you can define stable and unstable property. You want to say what does it mean that V is in a stable subbundle, or you want to say what does it mean that V is an unstable subbundle, and you can define it using this using the Jacobi vector fields. Namely, what you can do, you can say that the stable subbundle at this point V, so this is, sorry, VS, it's a curve. So stable subbundle at the curve V is just all Jacobi vector fields. So this Jacobi vector fields based at V along the geodesic gamma V, such that they're bounded in the future, such that if you look at them and they have some uniform bound in the future. And in the same way, you define unstable subspace at V as Jacobi vector fields, which are bounded in the past. Okay. So this type of sub-bundles, they actually can be defined for any manifold. You don't even care what the metric is. You can always define, you can say that this is stable and this is unstable. But what happens in negative curvature is that these things are precisely stable and unstable for the in the Anosov definition. And then in the early 70s, people looked at what does it so in particular Pat Eberlein, so Eberlein criterion for being Anosov. He proved this. So if you have a manifold MG, Riemannian manifold, and you assume that you have no conjugate points, and remember by Klinberg, this is actually a necessary assumption for being Anosov. So you assume that there's no conjugate points. No conjugate points. And then you're looking at the stable and unstable subspaces. And if you have any hope for the geodesic flow to be Anosov, the subspaces should be disjoint. So this is what he asked. And yes, intersect U, I want not an empty set, but just zero subspace, right? So it just gives you zero subspace. So they're transverse. They have a zero intersection at every point. Then Eberlein tells you that the flow is Anosov. Then the geodesic flow is Anosov. And this is if and only if characterization. You know, if a geodesic flow is Anosov, then Klinberger tells you that there are no conjugate points, and this is obvious, more or less, from the definition. So the difficult part is to actually prove this, which Eberlein did. So this is 1973, I think. And let's look at this condition a little bit. What does this condition actually say? Intersection empty simply means that, you know, you don't have Jacobi vector fields which are bounded in the future and bounded in the past, and at the same time are non-trivial. So this simply means no bounded Jacobi vector fields. So this is the Eberlein criterion. And actually a little bit later, also in the 70s, this condition that there are no bounded Jacobi vector fields simply means that from differential dynamics point of view, simply means that if you take a tangent vector and you flow it with your differential in forward time and in backward time, it does not stay bounded. And in smooth dynamics, this is called quasi-Anosov property. So this is called quasi-Anosov, let me put it in color, which was introduced by Manier. This is called quasi-Anosov property. Quasi-Anosov property. And generally speaking, if you're in generality of smooth dynamics, quasi-Anosov does not imply Anosov. But in this setting, in the setting of geodesic flow, Manier actually proved that quasi-Anosov property implies Anosov. So if you want, you can cross this out in the Eberlein criterion. So this is like maybe Manier late 70s, maybe 78. It was written down carefully by Ruggiero much later. So this is the Eberlein criterion. And now I would like to move to the known constructions of this Anosov matrix. So I'm interested in constructions of Anosov matrix which are not negatively curved. There are a few of those constructions known. I'm going to make a quick overview. But here is a simple thing that anyone can try doing. You just take a flat disk. So take a nice flat disk. You can do it, make it higher dimensional, but let's think about dimension 2. So take a flat disk. And when you glue some kind of color and you try to create this area defect to introduce some negative curvature. So you do this color such that towards the end of a color, you're introducing curvature -1. So you have curvature equals to 0 on the disk. And then you can write everything very explicitly in coordinates, and you can smoothly deform your curvature from 0 to curvature -1 on a slightly bigger disk. And then once you're on a slightly bigger disk, you can just find a hyperbolic surface with sufficient amount of space, and you put this disk inside of hyperbolic surface, and this really has to be Anosov. So you can do that. So you take this flat disk, doesn't matter what's the size. It could be a very big flat disk, and you put it into hyperbolic surface like that, and the geodesic flow is going to be Anosov. Intuitively, it's kind of pretty clear, right? Because you go here, you don't have any stable, unstable subspaces. Everything is sort of isometric. But when you arrive in negative curvature and your hyperbolicity kicks in, goes on for some time, when you return to the flat part, but flat part doesn't do anything bad. It doesn't like interchange stable and unstable directions. I'm sure this was known to Anosov and certainly known to Eberlein. Eberlein mentions something like that in his paper. So this is non-positively curved example. And of course, Anosov flows are structurally stable, so you can perturb your metric in situ topology if you want to introduce a little bit of positive curvature. You can create a little bit of positive curvature on this disk if you want. So this is a simple construction. How would the rigorous argument go here if you really want to try to write it down? So you're looking at this Jacobi equation, and you would like to apply Eberlein criterion. So you want to show that your geodesic flow is quasi-Anosov, meaning no bounded Jacobi fields. So you're looking at this Jacobi equation along the geodesic. It's like that. And then you do this beautiful trick, which is you go to Riccati equation. So you go from Jacobi equation to Riccati equation, which is just some variable manipulation. You say your new function u is j prime divided by j. Then you differentiate it, and you're getting a different equation. The equation is like that: u prime equals minus u squared minus k. And this is very nice because this is a first order ODE. And if k is a constant curvature, you have this nice phase portrait. So you have solution equals to 1. So this is for u. So 1 pretty much means that your Jacobi field grows as e to the t. And so it's bounded in the past. So this corresponds to the unstable subspace in terms of j. And then you have constant solution -1. This corresponds to e to the negative t for j of t. And this is bounded in the future. So this is your stable subspace. And then the phase portrait is very clear, right? It's what you teach your students in the ODE class. It looks like that. So this is what happens in negative curvature. Now we have this flat disk here. So this is not an autonomous equation anymore. This k depends on t, but you can still analyze this phase portrait pretty well. Namely, what happens is that you have the 0 line, u equals to 0. And at 0, you have u prime equals minus kt, and our curvature is non-positive, so it's greater or equal than 0. It could be 0, it could be positive, minus k. So what does that mean? That means that sometimes maybe you're flat here when you're going through a flat disk. But when at other times you're positive, and then maybe you're flat again. So this curvature 0, this is curvature greater than 0. But then you have to be positive again. You know, from the geometric construction, you know that you interchange. So for example, if you have a solution, the solution U, which crosses here, it goes into positive component, it will never cross back. It will never cross back because this vector field prevents you to do so. So it can be positive. Maybe you can come back to zero very close, but when eventually, even if you're close to zero, you're gonna have a positive bump again. And your solution would be positive enough. So you have that, but to show that J is unbounded, so to show that J of t goes to infinity, as t goes to infinity, you need to look at this integral. Let's say from some point t naught to t, u of s ds. This is equivalent. And you want to show that this goes to infinity. And because you always have some positive curvature, maybe you spend some time close to zero, you always get this bump, and you can show that this integral is positive. So this is how rigorous argument goes in this case. It's really useful that you don't cross zero line once you're on the positive side. So you can show that you either unbounded in the past or you unbounded in the future just by playing with this differential equation. So this was probably known to Anosov, but then a little bit later in 75, Gulliver made this construction much more sophisticated. Namely, he managed to put, instead of a flat disk, he took a rotationally symmetric spherical cap, and he actually did it in any dimension, not just dimension 2. So this is a piece of sphere. You just need it to be less than half to make sure there are no conjugate points. If it's half or more, then it's not going to be Anosov because there are conjugate points. And then Gulliver, in a very rotationally symmetric way, very carefully managed to explicitly, so he had this class of this cap. I guess it could be a little bit more general than a sphere, but it has to be rotationally symmetric. And then he managed to attach a collar in such a way that you go from curvature +1 to curvature -1. And when you do exactly the same trick by adding lots of negative curvature, and more or less the same argument goes through. It's kind of much more complicated now, but it goes through. And he had examples of Anosov flows like that. Examples of Anosov flows with spherical caps. Anosov flows with spherical caps. Then there is this Pew Donnay example. So this is Donnay Pew. This is a really fun example. Donnay Pew. So the point of this example is that you're getting a two-dimensional surface which you can actually put in three-dimensional space. So the metric here comes from the ambient three-dimensional space. So this is in 2003. If you have a negatively curved surface, you cannot put it in R3. So we asked this question, can you find an Anosov geodesic flow on a surface that's embeddable? And we had this beautiful idea that you take the surface, a sphere, just two-dimensional sphere like that. And then you put a slightly smaller sphere inside, and you kind of orient it in the opposite way, right? So you orient it like that. And then you drill many, many holes. So you drill many, many holes to introduce negative curvature. Yeah, first of all, you need your sphere to be of very large radius. So it's almost flat. So locally, it's almost flat, just a little bit of positive curvature here. And when they drill many, many holes to create lots of negative curvature, and they check the Anosov property. So this is the picture, and we even found this surface somewhere in nature. Pew Donnay example, and then there is a really beautiful example by Kurganov. So this is Kurganov, which kind of shows that these are not just curiosities. So this is Kurganov, probably 2019. So he looked at these linkages. These are just mechanical systems. So this is a picture of linkage. And if you work out the phase space of this linkage, you're going to get that this mechanical motion of this linkage corresponds to geodesic flow on this surface. So this is a picture in T2 cross R, and this is isometrically embedded. So you can see that, you know, most of the curvature there is negative, but when you have some positive curvature at places, but at the core here, the curvature is negative. And he shows that this linkage is completely chaotic by checking that geodesic flow on this is very high genus surface is Anosov. So this is, you have Anosov geodesic flow here. Also geodesic. Let me go to our theorem. So our theorem is, in a sense, is a generalization of this Gulliver construction. It's actually it's very technical, but at the same time, what I like about it is it's very general. So let me try to state it carefully. So theorem joined with Don Chen and Yerchenko. And what we do is the following. We take this domain, which you can think for now as a spherical cap. So some domain with boundary, sigma G. This is a compact Riemannian domain, which has spherical boundary. So boundary is a sphere of dimension 1 less, or it could be a union of several spheres. Could be union of 2 spheres or some finite number of spheres is also okay. And then we ask ourselves, can we put this domain into a manifold such that geodesic flow is Anosov? And first of all, we need to ask for no conjugate points, because this is a necessary assumption. So assume that sigma has no conjugate points. And then we also need to assume that the trapped set is hyperbolic. I'm going to explain in a second. Trapped set is hyperbolic. And the last assumption, this is a technical assumption, but it's really crucial, that this boundary is convex. So boundary is strictly convex. Strictly convex. Then the conclusion that you can extend it into Anosov flow. Then you can take this domain and put it isometrically into, you can extend the metric, you can put it isometrically on into some closed manifold such that the metric is just extension. So here M is a closed manifold, with Anosov geodesic flow. So phi t on the unit tangent bundle of M is Anosov. So this is a statement. So what are the examples? You can take all sorts of cap, and one advantage of our method is that we don't require any additional symmetry. So your spherical cap could be somehow skewed in some way. That's okay. And we also allow this trapped set. So what is a trapped set? For example, you can take a cylinder like that. You can take maybe. So I draw it in such a way that it has a little bit of positive curvature and a lot of negative curvature on the top, a little bit of positive curvature on the bottom. And when you see here, you're going to have a geodesic, and this is a trapped set, which never crosses the boundary. It's going to be unique geodesic here, right? So you're going to have a geodesic like that. And if that's not a hyperbolic, if that's not a hyperbolic periodic orbit, there is no hope that you can put it into an Anosov geodesic flow. So you need to require that the trapped set, so the trapped set lambda is just the set of tangent vectors to your domain. So V is tangent vector to your domain, such that if you shoot out a geodesic, the geodesic will never reach the boundary in forward and in backward time. This is a trapped set, and this is a necessary assumption that this trapped set has to be a hyperbolic set. So, and you can draw some more complicated example, like you can do an example like that, right? So here the trapped set is going to be complicated. You're going to have one geodesic going in this way and one geodesic going in that way, and then all the combinations, because you can shadow. So this is some non-trivial hyperbolic set in there. So our result applies to this type of domains. So this type of domains have been studied by people who do boundary rigidity and length rigidity problems. I'm going to say a few words about it. I don't think I can say much about the proof, but basically the very basic idea goes back to this. You write down this Riccati differential equation, and then the big issue is that because of positive curvature, you really don't have control. You move up, and then maybe you move down, and you move up, and maybe you move down, and you need to make sure that this integral goes to infinity if you want to show that your Jacobi field is unbounded. So the proof is unfortunately very technical, too technical to my taste, because it has many curvature estimates. And even in dimension 2, this is a new result. Even in dimension 2, it's non-trivial, and I don't think it was known before. But now I have what? I have maybe 5 more minutes, is it right?
Well, 5 is okay, yes.
Mm-hmm. Okay, so I'm just going to quickly mention 2 applications of this result. Let me see, what do I want to say first? So let me say a word about this boundary rigidity. So what's boundary rigidity? If you have a disk, you can associate this boundary function to it. You take a point P and you take a point Q, and you have a metric G here. So there is a unique geodesic connecting them, and you can look at the distance between P and Q. That's a boundary function. And the question is, can you recover the metric inside of a domain from knowing this boundary function? So this boundary function dg is from the boundary, so the sphere times the sphere, and maybe you want to remove the diagonal. So this is a function, and the question is, suppose, so question which many people worked on, and I don't think I can do justice to history of this problem, but the question is that if you have 2 metrics and the boundary distance is the same, probably under some condition, does it imply that G1 and G2 are isometric? So you get one metric just by isometric matrix using a diffeomorphism. And so one application that we have is that, and very recently they've been looking at usually at the domains which are simply connected, so which are basically disks. And recently Guillermo and other people, they started looking at domains like that, which has some non-trivial trapped set. And this problem is much more difficult when you have a trapped set, because now if you have 2 points, you need also a marking, because you can go from here to here like that, or you can go through the hole and come back. So you need a little bit more information. This distance is not unique anymore. So you need a little bit more information. You need kind of this marked function together with homotopy class. But the question still makes sense for this domains with topology, and people study it. So we have a small application in that direction. So application is that, suppose you have 2 metrics which are conformal to each other. Unfortunately, this Anosova extension does not help in general case, but if you have conformal, so you have one metric and you have another metric, so you just multiply your metric by a conformal factor, rho squared. So these are domains which satisfy our assumption. So this is satisfy assumptions of our theorem. I think I had 3 assumptions, 1, 2, 3. Then if we know that this distance function, the marked version of it for G, is the same as the distance function for rho squared G, then that actually implies that the metrics not only isometric, but they're actually the same as metrics. So this conformal factor has to be equal to 1. It has to be the same. So this was a really this is not hard to derive from our theorem, but it was known. A version of this was known before, a few years before us. Guillermo and Mazzucchelli established this result. We established it in 2018. Mazzucchelli, I think, like that. So we had it in 2018, same type of theorem. So this is one application. And second application is the Lifshitz theorem for domains. So Lifshitz theorem for domains. It's kind of funny because this Lifshitz theorem for domains is really important in this program of boundary rigidity, and people, geometers who work on this problem, we always call it Lifshitz theorem because we see analogy, because the differential equation, the ODE, is the same as in Lifshitz theory in hyperbolic dynamics. But I think before our work, there was no direct link between two theorems. So what is this Lifshitz theorem for domains? So suppose you have some function beta defined on the unit tangent bundle. And you assume that beta, so it's smooth. So smooth function, C infinity function inside of the domain. And you assume that on the boundary of the domain, it vanishes to high order, to some high order. And assume that for any geodesic, so you have this domain, and you connect any point A and B by geodesic gamma. So for any geodesic like that, if you integrate beta over gamma, so from A to B, then you get 0. Then Lifshitz is telling you that this beta is a solution to the, so that there is a solution to the differential equation. Then beta is actually derivative of some other function u, there x is the generator of a geodesic flow. So this is a geodesic flow generator. So this is exactly the same as Lifshitz theorem for Anosov flows, same equation. So so you can solve this equation, and u vanishes on the boundary as well to the same order as beta vanishes on the boundary. So now there is a link between these two Lifshitz theorem, namely what our theorem allows to do. You just take this domain, you extend it to an Anosov manifold, and then you extend your function beta by 0. So beta is some non-trivial function inside of the domain. You extend it by 0, and then it's very easy to see that you can apply Lifshitz theorem for the Anosov flow and get this conclusion for the domain. So basically what we have is that the classical Lifshitz for Anosov flows, implies this Lifshitz for domains in this setting. Lifshitz for domains. But again, this is not new. I should say that this is a theorem of Guillermo as well. So this is the theorem of Guillermo. So this is a step in one of his theorems about boundary rigidity. So this is Guillermo, probably in 2017. This Lifshitz theorem for domain. It was known much longer. I don't remember due to whom in the case when there is no trapping set. But if there is trapping set, it becomes more difficult. And it's only in 2017 that he proved it. For domains, now we have a completely different proof from his, which is always nice to have several different proofs. Okay, I think I'm going to stop here.
Thank you very much. So I prefer that we all thank the speaker. And are there any questions?
What about manifold M in your theorem? What about manifold M?
In here?
Yes.
No, it's a closed manifold. We constructed by hand. We constructed by hand.
Yes, I understand, but what topological structure? Could we say something?
Yeah, okay, sure, yeah. So basically the proof more or less goes like that. So we start with the sigma, right? Let me draw it like that. So it's domain with the boundary. This is sigma. And then you always worry about controlling the curvature, and you worry about, you don't want to create conjugate points. You have an assumption that you don't have conjugate points, but then you don't want to create more conjugate points. So we have several collars attached to it, and all the we are doing these different collars for different purposes, but I think there are 3 of them that we do for various different reasons. So we do one and then do the other one, in order to keep track of various estimates. But at the end of the day, it's exactly the same as Gulliver. You have this locally over here, the metric is just constant curvature -1. And once the metric is constant curvature -1, you just take some hyperbolic manifold of the same dimension. And if you have a hyperbolic manifold, you can always find, you can pass to finite covers and find a hyperbolic manifold which has arbitrarily big hyperbolic ball sitting in it. So you have this hyperbolic manifold N with a big hyperbolic ball, and you take this hyperbolic ball out and put all the stuff in. And this is what the manifold is. So it comes from a hyperbolic manifold.
And N could be any hyperbolic manifold or
as long as it has a point with a large disk, yes.
Okay, thank you.
Sure.
Can you put several of these domains?
Yes. So if we have, yeah, we can do several. Yeah, you can do something like that. Like you can have one domain over here, and maybe you have even domain. You can have several boundary components. So you have another domain which has two boundary components, and you can put all this together into a manifold with hyperbolic geodesic flow.
If there are no more questions, let's thank the speaker again, and thank you very much.
Thank you.
And we continue with our last talk for today in 11 minutes.
Andrei?
Yes.
Sorry, a question. You said that Guillermo also had proved this result of Lifshitz for these domains. So, but he or she, I don't know, Guillermo didn't use this. He didn't use this dynamics approach.
Yeah, he did it. No, it's more of a calculus proof. Yeah.
But is the construction is he construct the solution, or it is an existence?
In a sense, yes. In a sense, yes. Yeah, he constructs the solution. Yeah, the difference, we always work with Sobolev regularity. So formally speaking, I guess our theorem is new because his was in Sobolev and it does not apply ours because ours is, traditional CR plus
you
Hilbert.
go to Anosova technology, you go to the hyperbolic.
Yeah. Okay. But you see, this Lifshitz theorem for domain, it's actually kind of a little bit easier because, it's kind of, everything is compact. Everything is compact and you just integrate. You basically do calculus. If you have a disk, you do calculus and you recover the solution. But when with trapping set, it's really difficult because you go very far in trapping set, spend time there when you come back. So I think it was a difficult generalization that he did.
But he needs also that distrapping conditions. I mean,
he needs hyperbolicity. He need to make sure that it's kind of, it doesn't have any interior, the set, and he really uses hyperbolicity in some other way. I cannot remember right away how he does it, but he really relies on hyperbolicity of a hyperbolic set inside of it. So maybe, in some way his proof is not that different. Yeah.
And magically, it helps him for the calculations, you say. Okay,
yeah.
Nice. Thank you.
Andrei.
Yeah.
The example of Pure, and I do not remember who else, seems to be a little bit different, because there the part with positive curvature is much larger than.
Yeah, this example is totally different. It's a very fun example. Yeah, it's different. You're right. Yeah, because it's.
Do you think you can also generalize it?
No, I don't know. I'm not even sure what could be the statement of a generalization. But yeah, it's very different example. I'm sure there is some way to generalize it, but you can take something else instead of sphere. I'm sure it also would work. Like instead of taking a sphere sitting inside of a sphere, you can probably take a torus sitting inside of a torus. It's also going to work in the same way, but I'm not sure if it's makes sense to do that.
Hi, Andrei.
So
one potential question in this direction is, can instead of putting in the three-dimensional Euclidean space, can you do it for the three-dimensional spheres?
No, why not? Sphere is pretty much the same as Euclidean space with an extra point. Or you mean sphere with curvature equals to 1 or something like that? Oh.
Like curvature 1.
Oh, that's different, yeah. If it's some curvature close to 0, I'm sure it works. But if curvature is 1, yeah, I don't know. Yeah, that's a good question. Yeah, can you have a surface inside of three-dimensional sphere of curvature 1 such that geodesic flow is Anosov? Yeah, that's an interesting. Yeah. Okay, and Boris made a comment that he thinks that the basic example with the flat disk is probably Hopf knew it before Anosov. Yeah. Probably yes, except that Hopf didn't know what Anosov flow is. But yeah.
guess we are waiting for 1 more minute.
Okay.
And yes, it's 8 p.m. Moscow time. So it's my pleasure to pass the word to Lingru Ge for the last talk for today. Lingru, please.
Okay, thanks for the introduction. I'd also like to thank the organizers for the invitation. And today I will talk about multiplicative Jensen's formula and quantitative global theory for one-frequency Schrödinger operators. So first of all, let me introduce several words in this title. So first one is multiplicative. This word comes from the famous multiplicative ergodic theorem. And we all know that ergodic theorem says if we have a triple pair, this x mu t is ergodic, and f is a measurable function, then you will have the space average of this f equals to the limit of the right side for almost every x. So this is the classical ergodic theorem. And there are many versions of multiplicative ergodic theorem. Here we mention the Kingerman's multiplicative ergodic theorem. The difference is you replace this measurable function by a measurable matrix. Then you consider 1/n, the logarithm of the norm of the product of this matrix. And this limit still exists. This is the multiplicative ergodic theorem set. And since this matrix multiplication is in general not commutative, so the limit no longer equals to the space average as in 1. But this limit serves as the analog rule as the space average here in the first equation. And we have a special name for this limit. It is the so-called Lemma exponent. Okay. So now let's explain the second word, the Jensen's formula. And we all know the Jensen's formula is a very fundamental formula in complex analysis. It says, given an analytic function in a region in the complex plane, which contains the closed disk of radius r about the origin, and assume inside this disk you have n zeros, a1 to an, and f0 does not equal to 0, then for any epsilon here, you can consider this logarithm, the normal f, the integral of this function. The Jensen's formula says it can be fully represented by the zeros of this function inside this circle. Okay, certainly you can rewrite this, the right side of this formula as the following way. Okay, it is an integral plus some blah blah plus some linear function, a piecewise affine function in epsilon. Okay, so suppose you define this I epsilon equals to the integral of the logarithm, the normal f on this circle, the radius equals to e to epsilon. So you view it as a function of this epsilon. Then it is obvious that from the Jensen's formula, it is a piecewise affine function in epsilon. And the turning points of this affine function are exactly negative log AI. AI as zeros inside this circle. Okay, this is the classical Jensen's formula. Next, let's explain the third word. So our theory is for one frequency Schrödinger operator. Okay, this Schrödinger. So first, let me introduce the one frequency Schrödinger cocycle. And if it is in a random case, Victor has already introduced as the definition of the random Schrödinger cocycle. And now we consider our model is for the quasi-periodic case. So this is a very special ergodic dynamic system. So you just take X in this ergodic system, you take X to be the unit circle and the mu to be the Lebesgue measure. And this transformation to be the irrational rotation over the unit circle. Also, this matrix A theta is very special. It is of this form. It is a so-called Schrödinger cocycle. And here V is a 2 pi periodic analytic function on the strip. Okay, this is an analytic SL2R cocycle. Then certainly you can, since this is an ergodic theorem, ergodic system, certainly you can apply Kinkelman's ergodic theorem to the product of this A theta. This is a special A theta, SL2R matrix. And by Kinkelman's ergodic theorem, this limit exists for almost every theta. And we denote this limit by L epsilon E. It does not depend on theta. So this is the so-called Lemma exponent for Schrödinger cocycle. Actually, if you take A theta to be a special form, there is no -1 and 1 here. It only equals to this form. Then you will see this product of this, the product of this matrix is commutable. So the Lemma exponent reduces to this I epsilon, the integral of the logarithm of the norm of this E minus V here. So if you, this is A theta is of this special form, then L epsilon E reduces to I epsilon. So from here you can see L epsilon E is a 2-dimensional analog of this I epsilon defined in this Jensen's formula. Okay, so our result is for this is to prove a Jensen's formula for this L epsilon E. Since it is this limit is ensured by Kinkelman's multiplicative ergodic theorem, so we call this Jensen's formula the multiplicative Jensen's formula. And but actually we found there exist dual Lemma exponents. Later I will explain what is the dual Lemma exponents, denoted by L1 hat to Ln hat, such that if this alpha is irrational, so if it is an irrational rotation over the unit circle, and you consider Schrödinger cocycle, you will have this L epsilon E. This L epsilon E exactly has an analog of the Jensen's formula here. So for this function, we have a Jensen's formula here. So actually, L epsilon E plays a role as this integral. And it equals to L0E. This L0E plays a role as this integral. And minus blah, blah, this Li hat E plays the similar role as logarithm the norm of AI. AI is the zero of a negative function in the Jensen's formula. Actually, later I will explain that this Li hat E is not artificial. It is a natural quantity, comes from a dynamic system. And this Li hat E also has nice dynamic properties. For example, they are continuous in energy E. Also, they are invariant under continuous conjugations. Actually, they are Lemma exponents of certain dynamical systems. Okay, this is the multiplicative Jensen's formula for this L epsilon E. Next, let me introduce what does this dual Lemma exponent mean. Actually, we can consider a special case, the trigonometric polynomial case. In this case, it is very clear what does this Li hat E mean. So this is the Schrödinger orbiter. And so the trigonometric polynomial case means you take V to be a trigonometric polynomial, not a true real analytic function. And for this operator, we can define the dual in the spectral side. We can define the dual operator of this operator. It is a 2D order difference operator. And actually, roughly speaking, the second operator is the Fourier transformation of the first operator. And if you consider the eigenequation of the second operator, it naturally induces a family of quasi-periodic GL2DC cocycles. So here, L is the 2D by 2D matrix. So once you have a 2D GL2DC cocycle, you can define 2D Lemma exponents. But this system is very special. You will find these 2D Lemma exponents come into positive and negative pairs. So actually for the SL2R case, we have two Lemma exponents. One is positive, one is negative. And in this case, you have 2D Lemma exponents. They come into positive and negative pairs. And we can, in this case, we can prove that this Li hat E are exactly the Lemma exponent of this dual cocycle, or this GL2D C cocycle. So to formulate this theorem for the trigonometric polynomial case, we can group the Lemma exponent of this cocycle as gamma n1 to gamma nl with multiplicity ni minus ni minus 1. So here we arrange the Lemma exponent from small to large one. Okay, then you can formulate this theorem, the multiplicative Jensen's formula for this Lemma exponent in this way. This is piecewise affine function. So we can take a picture of this function. You will find all these distinct Lemma exponents are exactly the turning points of this piecewise affine function. And when you go through the first turning points, the slope of this piecewise function will increase n1. And n1 is exactly the multiplicity of this gamma n1. And when you go through the second turning points, gamma n2, the slope will also increase n2 minus n1. And n2 minus n1 is exactly the multiplicity of this gamma n2. So for this piecewise function, these distinct Lemma exponents are exactly the turning points, and the increment of the slope on each piece is exactly the multiplicity of each distinct Lemma exponents. Okay, so this is a very interesting phenomenon because it is exactly the same. This Lemma exponent L epsilon E displays exactly the same phenomenon as this phenomenon in the Jensen's formula. So next, we would like to say, more importantly, this formula is not only interesting itself, it also plays a very important role in the study of the spectral theory for quasi-periodic Schrödinger operators. Now let me introduce to you what is the Schrödinger operator. So the one frequency Schrödinger operator are given by this way. So the first term is the discrete Laplacian, and the second term is a multiplication operator. This V, as we mentioned above, it is a 2-pi periodic and real analytic function. And the relation between the Schrödinger cocycle and the Schrödinger operator are given by this way. Suppose you have a formal solution of this eigenequation. Then you will find a second order recurrent relation for this solution. Here, A theta is exactly the Schrödinger matrix. Okay. We call this pair alpha A the Schrödinger cocycle. Next, the next theorem gives the relation between the dynamic property of this cocycle and the spectrum of the Schrödinger operator. Okay, for this Schrödinger operator, we can certainly define the spectrum of this operator. They are the energies such that h theta minus ei not invertible. And a well-known result is the spectrum of this h theta does not depend on theta if this alpha is irrational. And we can define this spectrum by sigma. Also, for this cocycle, we can consider the nth iteration of this cocycle. They have this form. It means this an theta equals the product of this matrix. For this cocycle, a very well-known definition is called the uniform hyperbolicity. It says this cocycle, this is the SL2R cocycle. So uniform hyperbolicity means it has a continuous, there is a continuous splitting of C2 such that, so for any theta, there's a continuous splitting depending, this is the most contrast direction. This is the most expanded direction. They both depend continuously on this theta. Okay, this is the definition of uniform hyperbolicity. And the relation between this cocycle and the spectral property of the Schrödinger operator are given by the famous Johnson's theorem. It says this cocycle is uniformly hyperbolic if and only if this energy E, so in this A theta, there's energy E. This energy E is not in the spectrum. So this is the first relation between the dynamic property of a cocycle and the spectral property of an operator. And next, I'd like to introduce to you a recent progress on the spectral theory for one-frequency Schrödinger operators. It is Avila's global theory. Avila consider the Lamb exponent of the complexified cocycle. So this is the Schrödinger cocycle. And this L epsilon E is exactly the L epsilon E we defined, appeared in our multiplicative Jensen's formula. And this L epsilon E plays a foundation in Avila's global theory. He finds two fundamental facts based on this, based on the analysis of this L epsilon E. The first fact is he proved that for any fixed energy E, if you consider L epsilon E as a function of epsilon, then it is a even convex piecewise affine function in epsilon. And the slope of each piece is an integer. So the proof of this fact is highly non-trivial. It plays a very important role in Avila's global theory. But as you can see, our multiplicative Jensen's formula is exactly a quantitative version of this theorem. We not only not only prove this is a piecewise affine function, but also we give the exact turning points of this piecewise affine function. And we also give the exact slope on each piece based on the multiplicity of its dual Lamb exponents. Okay, another fundamental fact I will find is if one define omega E in this way. So in the following, I will omit L, actually this is L0, L epsilon E minus L0 E, I will omit 0 here. And if one define omega E in this way, the so-called, give a name for this quantity, it is the acceleration. He find the dynamic property of alpha A is totally determined by LE and omega E. Actually, we all know only the Lamb exponent cannot govern the dynamic behavior of this alpha A. But if we add one more quantity called this omega E, then this dynamic behavior of this cocycle is totally determined by these two quantities. Okay, this omega E is nothing but the slope of the first piece of this function. Okay, for example, for this picture here, you will find omega E equals to 0. Actually, it equals to the slope of the first piece of this function. Okay, since our multiplicative Jensen's formula gives a quantitative version of this epsilon e, it's natural to give some quantitative estimates or characterization of the objects appeared in our last global theory. So the first thing we can do is a new characterization of uniform hyperbolicity. Okay, the first definition is the classical definition of uniform hyperbolicity. The second one is proved by Avila. He proved that this cocycle is uniformly hyperbolic if and only if the Lemma exponent is positive and the acceleration equals to 0. So this is a new characterization of uniform hyperbolicity for analytic SL2R cocycles. And we give a new way to, by our multiplicative Jensen's formula, we give a new way to characterize this uniform hyperbolicity for this Schrödinger cocycle. We can prove this cocycle is uniformly hyperbolic if and only if the Lemma exponent is positive and the minimal Lemma exponent. So this R hat 1e means the minimal Lemma exponent of its dual system. Here is the minimal Lemma exponent of its dual system. It's positive. Okay, so we can replace this acceleration by the minimal Lemma exponent of its dual system. From this, you can see uniform hyperbolicity is stable under perturbation because in this case, we can prove all Lemma exponents are continuous. So the positivity of Lemma exponent is stable under perturbation. Also, we can give a new calculation of the non-uniform hyperbolicity. And first, the definition of non-uniform hyperbolicity is the following. If the Lemma exponent is positive and this cocycle is not uniformly hyperbolic, then we say it is non-uniformly hyperbolic. Actually, with this definition, you can divide the whole real line into 3 parts: the uniformly hyperbolic part, the non-uniformly hyperbolic part, and the 0 Lemma exponent part. And I will prove that this cocycle is non-uniformly hyperbolic if the Lemma exponent is positive, then and the acceleration is larger than 0. So this is the positivity of the acceleration is the difference between non-uniform hyperbolic and the non-uniform hyperbolicity and uniform hyperbolicity. And we also give a new way to describe this non-uniform hyperbolicity. We can prove this cocycle is non-uniformly hyperbolic if and only if the Lemma exponent is positive and the minimal Lemma exponent of its dual system equals to 0. From here, you can see non-uniform hyperbolicity is more complex than uniform hyperbolicity because its dual system will have 0 Lemma exponents. Okay. Since acceleration plays a very important role in our global theory, actually our multiplicative Jensen's formula can give a quantitative characterization of this acceleration. We can prove that the acceleration is totally determined by the multiplicity of the minimal Lemma exponent of its dual system. So we have 2 cases. If the minimal Lemma exponent, this R hat E is larger than 0, then the acceleration equals to 0. If R hat E equals to 0, then omega E equals to the multiplicity of this R hat E, R hat 1E, so the multiplicity of the minimal Lemma exponent. And from here, you can also see this omega E is an upper semi-continuous function in E, because if you perturb this energy E a little bit, then the number of 0 Lemma exponents will only decrease because positive Lemma exponent is stable under perturbation. So it is an upper semi-continuous function in E. And another fact is if omega E becomes larger, then the more Lemma exponents its dual system will have. and the more complex its dual system is. So this coincides with the spectral side. In the spectral side, if the acceleration becomes larger, then the spectral phenomenon will become more complex. So from this dynamic side, we can also see this phenomenon. And the last one is a very interesting phenomenon for the dual system. We can actually prove that the dual system, it is a GL2D cocycle. We can prove this cocycle is partially hyperbolic. That means we can decompose. This means this is the trigonometric polynomial case. We can decompose the whole space C2D into 3 parts: the most contracted direction, and the zero center direction, and the most expanding direction. Moreover, the dimension of the zero center direction equals to 2 times the acceleration. So the acceleration will measure the complexity of this zero center direction. Okay. So the above results are all about positive Lemma exponent region. So actually, in Avla's global theory, he can divide all energies or real energies into 2 parts. The first part is the positive Lemma exponent region. So for this part, based on the positivity of the acceleration, we have 2 non-uniformly hyperbolic part and the uniformly hyperbolic part and the non-uniformly hyperbolic part. Similarly, for the zero Lemma exponent region, we also have two definitions based on the positivity of the acceleration. If the acceleration equals to 0, then we say this energy is subcritical. If the acceleration is larger than 0, then we say this energy is critical. And there is a famous conjecture called the almost reducibility conjecture. It says this Schrödinger cocycle is almost reducible if and only if the acceleration equals to 0, or if and only if it is uniformly hyperbolic or subcritical. So as you can see here, the acceleration, positivity of the acceleration plays a very important role here, because the dynamic behavior are totally different for zero acceleration cocycles and positive acceleration cocycles. And we also give a new calculation of the zero Lemma exponent region. So we can prove this energy is subcritical if and only if the Lemma exponent equals to 0 and R hat E is positive. So this is the minimal Lemma exponent of its dual system. And this energy is critical if and only if both the Lemma exponent of the original cocycle and the minimal Lemma exponent of its dual cocycle are 0. So it seems you can also see here, the critical case is the most complicated case because both the original system and the dual system has 0 Lemma exponents. Okay. Next calculation is our multiplicative Jensen formula give a new quantitative estimate of the so-called subcritical radius. So the subcritical radius is defined in this way. So, okay, the subcritical case you can see in this picture. So this is the subcritical case. And the subcritical radius equals to the maximum epsilon such that L epsilon equals to 0. So the maximum here of this flat piece, the first piece is a flat piece. So the maximum epsilon such that L epsilon equals to 0. So it is the first turning point. So this is the so-called subcritical radius. And we can prove that this subcritical radius equals to the minimal Lemma exponent of its dual system. Actually, we all know the R hat E is related to the localization length of this dual operator. So this corollary established the relation between the subcritical radius and the localization length for its dual operator. And this this characterization of the subcritical radius in some sense is important because we find that for the almost material orbiter, later I will explain what is almost material orbiter. For this orbiter, this exact value of this subcritical radius is related to several optimal spectral estimates. Okay, this is the several new characterizations or quantitative characterizations of the objects appeared in Avela's global theory. Actually, I'd like to say the final aim of the global theory is to solve the spectral problems in quasi-periodic, in the field of quasi-periodic shorting orbiters. So let me say a little bit about the motivation of the global theory. So we will consider the almost material orbiter. So for this orbiter, you just take this v theta to be 2 lambda 2 cosine 2 pi theta. And for this orbiter, there's a famous metal insulator transition for this orbiter. So if lambda is smaller than 1, then this orbiter has purely AC spectrum, absolutely continuous spectrum. If lambda equals to 1, then this orbiter has purely singular continuous spectrum. And if lambda is larger than 1, then this orbiter has pure point spectrum for almost every alpha and theta. And actually, the global theory, when you apply Avela's global theory to this orbiter, you will find for the first region, if lambda is smaller than 1, then all energies in the spectrum are subcritical. So subcritical is related to AC spectrum. And if lambda equals to 1, then you will find all energies are critical in the sense of Avela's global theory. So critical is related to singular continuous spectrum. And if lambda is larger than 1, then all energies are supercritical. So supercritical is related to pure point spectrum. So the Avela's global theory is closely related to the spectral property of the shorting orbiters. Actually, based on our multiplicative Jensen's formula, we can give more dedicated results about more general shorting orbiters than beyond this almost material orbiter. Okay. Finally, I'd like to talk a little bit about the proof. So the central idea in the proof is since we need to consider the Lamb exponent of the complexified cocycle, so it's natural to consider this complexified shorting orbiter. So this orbiter is no longer self-adjoint. And a very crucial observation is for this orbiter, we can still define the dual orbiter of this orbiter. And the classical duality is defined for the case when epsilon equals to 0. And we find when epsilon does not equal to 0, we can still find the duality of this orbiter. Moreover, for the original orbiter, if epsilon equals to 0, if we denote this cocycle by alpha L, so we mentioned this at the beginning. So this, if you consider when epsilon equals to 0, if you consider the dual orbiter, it induces a GL2DC cocycle. This is alpha L. And for the case epsilon does not equal to 0, you can also induce a cocycle, GL2D cocycle, alpha L epsilon. And a very crucial observation is there is a simple relation between this cocycle, this alpha L epsilon, and the original cocycle alpha L. This is the cocycle corresponding to the non-complexified cocycle. This is the cocycle corresponding to the complexified orbiter. So there's a simple relation. This L epsilon, this is a matrix, it equals to here the right side. The second one, P inverse is just similar of L. Here we need to times some scalar e to epsilon. So there's a very simple relation between L epsilon and L. So this simple relation will give a relation between the Liam exponent of this cocycle alpha L epsilon and alpha L. So also we mentioned this at the beginning. If we denote gamma 1 to gamma t, so this cocycle is a 2D by 2D matrix. It has 2D Liam exponents and come into positive and negative pairs. And if we denote gamma 1 to gamma d, the non-negative Liam exponents of this original cocycle alpha L, then by this simple relation here, we will know the Liam exponent of alpha L epsilon are exactly gamma j plus epsilon. Since this similar will not change the Liam exponent, this scalar multiplication will only increase each Liam exponent by epsilon. So there is a relation between the Liam exponent of alpha L epsilon and alpha L. Also, there is also a relation between the Liam exponent of the original Schrodinger cocycle and the dual cocycle. In the case epsilon equals to 0, Pugh and Harrow proved this. The Liam exponent of the original Schrodinger cocycle equals to the sum of the non-negative Liam exponents of its dual system. Okay, but this proof is based on some spectral result. It only works for self-adjoint operators. So when epsilon equals to 0, this is a self-adjoint operator. So one can use the spectral identity, something like this. But this proof no longer works when epsilon does not equal to 0, because it is now a non-self-adjoint operator. But we can prove an analog. We can still prove an analog of this formula when epsilon does not equal to 0, based on dynamical system methods, and it's a combination of the dynamical system methods and spectral method. The so-called, we will develop a generalized Kotani theory. So the general idea is when epsilon does not equal to 0, one can still prove the Liam exponent of the original Schrodinger cocycle equals to the sum of the non-negative Liam exponents of this dual system. So here now the dual system is alpha L epsilon, not alpha L. And for this system, we have already said here, the Liam exponent are just the Liam exponent of the original system plus epsilon. So you will find some negative Liam exponent will become positive. So when epsilon is very large, it's a very large positive number, some negative Liam exponent will become positive because this negative gamma j plus epsilon are the Liam exponent of this system. So you will find when epsilon grows from 0 to infinity, there will be more and more positive Liam exponent for this system. So this is actually exactly the same phenomenon appeared in Jensen's formula. Now we can take a look at this Jensen's formula. In this Jensen's formula, you can see when you enlarge the radius of the circle. So here, when you enlarge the radius of this circle, there will be more and more zeros. So for this theorem, you can see when there are more zeros, then the slope of this piecewise function will increase. So when epsilon goes through this log AI, then the slope will increase. So this is exactly the same phenomenon appeared in Jensen's formula. Okay, so until now, I only talked about the trigonometric polynomial case. Since I assume this is a trigonometric polynomial, then the dual system is GL2D. We can induce this GL2D cocycle, so you can define the Liam exponent. So a more interesting question is, what happens if the potential is a real analytic one? And in this case, we still have orbital duality, but this is the difficulty is this is an infinite order difference operator. So one can no longer induce a cocycle. So one cannot even define a Lemma exponents. And the natural idea is to approximate this potential V by trigonometric polynomials, because in the trigonometric polynomial case, we can define the Lemma exponent. Then you define the limits of the Lemma exponent in the trigonometric polynomial case as the Lemma exponents in the real analytic case. So this is something very difficult because even the existence of the limit is not known. But by an elegant application of our multiplicative Jensen's formula for the trigonometric polynomial case, we can prove that the limits of the Lemma exponents in the trigonometric polynomial case exist, and they can serve as the Lemma exponents of the real analytic case. And exactly, it is those limits that determine the behavior of the complexified Lemma exponent of the epsilon E in the real analytic case. Okay, this is the general idea. First, you deal with the trigonometric polynomial case. Then you show the limit exists, and then you prove the case for the real analytic case. Okay, I think I have run out of time. Thank you so much for your attention.
Thank you very much. Let's thank the speaker.
Thank you.
And are there any questions? If not, well, I guess we had a really fruitful day today. So I suggest that we thank the speaker again and thank all the speakers of the day. And well, and Lysha, what time are we?
Tomorrow we start at 1 p.m. Moscow time, and you can see this in the schedule. And
oh yes,
tomorrow evening at 7 p.m. Moscow time, we have the session when anyone can share his impressions of meetings with Anosov, talks with him, and so on. So see you tomorrow.
See you.
Thank you.
See you.